Welcome to the course Yara, Malware Analysis and Threat Detection. This is really a course that's built around helping defensive blue teams better use Yara in terms of helping them with malware analysis and threat detection. Right now, there are so many different types of cyber attacks that are happening. Yara is a powerful pattern matching tool that can help security professionals detect and defend against some of these types of attacks. Yara is built around being able to use a set of rules, syntax that's easy to understand, to define patterns in files that you can match against and detect when you have potentially malicious software on your hands or there's a threat in your environment. Whether you're just getting started with Yara or if you have a lot of experience in security, this course will help you improve your knowledge of how you can use Yara to defend your network. It's going to teach you how to write Yara rules, but more importantly, it's going to teach you what to look for in different threat situations. By the end of the course, you should have some experience writing Yara rules, conducting malware analysis, and really be able to improve the defensive capability of your organization, improve the skills that you have to bring to bear in doing your job day to day, whether it's malware analysis or threat hunting. Now, in order to do this, we've divided the course into several sections. Section 1 and 2 is going to be the introduction, and we're going to set the fundamental concepts of Yara and malware. We're going to show you how Yara plays into the ecosystem of malware development, deployment, and detection, as well as threat hunting. We're going to talk about how you can analyze files, you can analyze memory, you can integrate with security tools within your environment, and how you can extend Yara. Section 3 and 4 is where we're going to dig into writing Yara rules, and we're going to talk about how we can develop some of our own testing tools so that we can prove out the validity and the integrity of the rule set that we're writing. And then the main event of the course is really sections 5 through 13. This is where we approach defending against threats and malware from a cookbook style, where we will take real-world scenarios, real-world situations that you would want to be able to identify and detect within your network. We're going to talk about how you can identify the content of files and the file type, how you can use Yara to look for potential network recon activities that may be embedded inside files. We'll talk about spying and data collection and how some files that you would inspect may have commands built into them in order to do things like read the clipboard, sniff audio. We're going to look at how you can detect remote access tools. We'll talk about crypto, ransomware, and shells, giving you the tools, the capability, the understanding of how you can use Yara to determine whether a target file may contain this capability. So let's go ahead and get started. By the end of this course, we hope that we're putting you in a position where you're just one step ahead of the bad guys. As you get started with this course, it's important to understand that the course is built around what we sometimes call a cookbook structure. There are a few sections in the beginning of the course that are fundamental. They really set the stage. They outline some basic concepts, and they help make sure everybody is coming to the course with more or less a common set of knowledge and understanding. But after that, things change, and most of the course is going to be focused on different use cases, and we talk about how Yara can be used to support malware analysis and threat detection in each one of these sample cases. Each lesson is going to be based on a use case, and they're all going to follow a similar structure. First, we're going to talk about the objective and the approach. This is used to help set up the objective, the parameters, the approach for testing with our Yara file. And this is where we talk about our goals. We state the conditions of testing and what we're trying to accomplish in terms of demonstrating the vulnerabilities that we may pick up on, the issues that we may pick up on in the inspection of each file. Now, a key takeaway from this course is understanding how we meet the rule objective. This can't be stressed enough. This is the most valuable part of the course. By the time we finish the approach, you should understand what we're doing, why we're doing it, and how it works. You'll find over time that the Yara syntax is very understandable, very readable. It almost becomes mechanical and second nature to write rules. The value comes in understanding the patterns that we specify, why we specify them, and how they relate to each use case. That's the value add of this course. That's the most important part. So if the objective and the approach are heavy in theory, then the practical part of the course is the section on rule development. For each one of these use cases, we're going to go line by line through example rules and talk about how the Yara syntax can be used to build a rule that meets that particular use case's objective. And then finally, we are going to show the results of applying our rule against a sample test file. Along the way, we're going to make sure that we highlight the need for positive and negative test cases. That way we can ensure the validity of our Yara rule. We make sure that it has the proper function and we have results that have a high level of integrity and dependability. And to do this, we're going to use a couple of different test approaches. In some cases, we will run our Yara rule against a static file. Sometimes we'll run it against a file that's executing and inspect the memory. Other times it'll be against a simple string extract. In any case, you'll be able to see the rule run against a sample file and see the results. So let's go ahead and get started. Before we get any deeper into the course, we do need to pause and spend a moment talking about ethics. This is the shortest, simplest slide in the course. It's also the most important one. We're the good guys here. Remember, knowledge is neutral. What you do with knowledge needs to be morally, ethically, and legally correct. Some of the topics that we talk about in this course can be used for good or evil. If you're here for good, if you're here to learn how to protect your network, your computing assets, then please continue. If you're not here for those reasons, if you're here for malicious, immoral, unethical, and illegal purposes, then stop now. The shortest slide, the slide that is very simple, but also the most important slide in the whole course. If you want to follow along exactly with the course, then consider having these tools installed in your lab environment. You can use any text editor to write Yara rules. You can also use any text editor for putting together a static file of strings that you can use during your testing. You can also use virtually any compiler that would generate C# code for you. And these are some of the components that are going to be in this course. We're going to use Visual Studio to write some test harnesses for us, some utilities that we can run that will assist us in having a test file that we can execute our Yara rules against. Another way that we're going to test our Yara rules is to create a static text file, and we can use Notepad for that, Notepad++, virtually any text editor. And then when it comes to actually writing the Yara rules, we're going to be showing them in Visual Studio Code. You can use any text editor or code editor for that as well. But if you want to follow along, those are the tools that you have installed. Additionally, we are going to use the Strings64 utility from sysinternals. This is a tool that allows you to extract strings from a binary file, another way in which we're going to conduct some testing. And then finally, you'll need Yara installed. In this case, we've got Yara 64, the 64-bit version of Yara installed, and that's what we'll be using in the course. As we start to talk about how we can use Yara for analyzing malware, sometimes it helps to take a step back and make sure everybody's on the same page in terms of understanding malware and some of the common types of malware that you will face. Malware is software that is designed to disrupt, damage, or gain unauthorized access to a computer system or data. And there are a number of different variations of malware. For this course, we are pretty much going to refer to malware in a very generic sense. The only time we're going to really deviate from that will be when we talk about ransomware, spyware, because we've got a few sections of the course dedicated to finding those types of threats. Oftentimes, people just simply refer to malware as a virus. Well, a virus is a specific type of malware. It's capable of replicating itself in order to infect other files. And that's one of the key characteristics about a virus. It replicates, and it takes human interaction in order to make this replication happen. Now, viruses are typically delivered through a binary executable file that the user will click on, and that's the human interaction element of this. When the user executes the file, then the virus spreads. This is very different from a worm. A worm is self-replicating. It does not require human interaction, and it will spread very quickly through a network without assistance and without intervention from people. So that's a key difference between a worm and a virus. Unlike a virus, there is no triggering event with a worm. A Trojan is another subclassification of malware. A Trojan is deceptive. It runs under the disguise of another more legitimate program. And it doesn't reproduce and it doesn't spread like a virus or a worm. Instead, it typically creates some type of backdoor for remote access and remote control. Ransomware is yet another type of malware, and this one's all about the money. The goal is extortion and payment of ransom in order to get your data back. Typically, it blocks access to files through a cryptographic means. It will encrypt those files and offer the key in exchange for payment of the ransom. So you have to make a decision there. Are you going to pay or not pay? That's sort of the key question. And if you do pay, then theoretically you would get a cleanup utility or the key back in order to restore your files and gain access. Just remember, you're dealing with the bad guys here, so they're not honest to begin with. And finally, we've got two other types of malware: spyware and bots. Spyware, sometimes called adware. The goal is to gather information about your user, and this can be used to support advertising. You try to harvest this data and sell it, collect intelligence, browsing history, online activities, and so forth. So it's really about disclosure of information. And the final type is a bot. It's obviously derived from the term robot, and it refers to a process that is automated. Now, bots are not always malicious in nature, but they can be if they're developed for evil. They can be part of a command and control infrastructure for flooding, denial of service type activities, and so forth. And botnets, they are a collection of individually compromised systems that work together in coordination through a command and control center in order to focus on a specific task. They all work as one large swarm of bots. So these are the types of malware that are out there. We're not going to draw too many distinctions between them except for the spyware and ransomware aspects of it. For the most part in this course, we're just going to refer to malware collectively because we're going to be looking for some of those indicators that a file that we're inspecting may have some capability or motive other than what it appears to be on the surface. One way that malware authors will attempt to avoid detection is through making minor but functionally equivalent changes to their malware code. The diagram on this slide illustrates the process. We know that hashing can produce a unique fingerprint of a given file, and that's how a lot of detection approaches work, where a piece of malicious software will have a hash value calculated for it, and then as files within a system are inspected, they're hashed and compared against that particular value. When a match is found, then it is assumed that we have a positive hit on a piece of malware. It's all based around getting that unique fingerprint. Now, what happens if a malware author makes a very small but functionally equivalent change to the code? Then that hash value will no longer match, yet the payload will still be the same. So over time, we collect all of these different hash values of known malware specimens. However, if the malware author makes a functionally equivalent change to that malware, the hash will never recompute to be the same value, and we will allow that piece of malware to slip through our defenses. This is the shortcoming of hashes. Hashes are great for developing a unique fingerprint for a specific file, but any changes within that file will throw the hash value off, and we will no longer have a match. So making these small changes can allow a malware author to avoid detection. What's the solution? Well, it's pattern matching, and that's where Yara comes into play. You can see here in this example, we've got pseudocode that represents the source file or the source code for a piece of malware. Line 1 is some filler code. Line 2, this is where we do the bad thing. This is the malware payload in our example. And 3 is a bit more filler code just to complete out the example. We would build that, and then we would derive a hash value from it. Now, if we make a minor change to that code, but we keep the functionality the same, we can avoid detection with a different hash value. Look at the second example. We still have some filler code, but then we create a function called doIt, and inside that function we have do the bad thing. Then we have some more filler code, and then we've got a line that calls our doIt function. We build that, we hash it, and we get a different hash value. Yet the same bad thing happens no matter which set of code we use. And towards the bottom of this slide, we have the pattern that we're matching on with a Yara rule. Look at line 6. That's the pattern that we try to match on, do the bad thing. So no matter where that line of code is, after the build, when it's embedded inside our executable, we can search for that particular string value. So that's the power of pattern matching and how it exceeds the capability of hash values in detecting these minor code changes. Of course, this is a highly illustrative example, but it's to drive that concept home that the changes to code throw off hashing, yet pattern matching is still potentially effective. This lesson is going to answer two key questions. What is Yara and where do I get it? Well, Yara is a utility that was designed back in 2013 by Victor Alvarez of VirusTotal. It's a tool that's designed to be used for pattern matching, and it's open source now. You can obtain the source code from GitHub. You can install it. It's out there in the public right now. So Yara, the name, is actually an abbreviation. It comes from yet another recursive acronym, or yet another ridiculous acronym, whichever way you want to look at it. That's what the Yara name was based on. And Yara allows you to find a number of different rules that can contain pattern matching and pattern identification, conditional logic, and more. These rules can be applied to a file for analysis. They can also be applied to a process that is running in memory for analysis. So this really fits well within the toolbox that a threat hunter needs or a malware analyst needs in order to take a look at a file or take a look at a process that's running in memory and try to discern if it's malicious or not, whether it's a threat or not. Some of the other benefits of Yara is that it's very easy to integrate with existing security tools, and it's very extensible. So it's a really nice fit for incident response teams, anybody that's got an analyst role or an incident responder type role. This is something that you need to know about. So now you're thinking Yara's cool. Where do I get it from? Well, one of the best ways to get Yara is to go directly to the source. We've got the GitHub reference here where you can get the latest version. We're going to be working with the Windows version in this course. There's a 32-bit and a 64-bit. You'll see in the lab as we run our rule set against a target file, we're going to be specifying Yara 64. There are a couple of components of Yara. You've got Yara.exe, 64 to 32, whatever flavor you choose to use. And then you've also got Yara C. That is the Yara compiler. You can compile Yara rules, and that will give you some performance benefits. For the most part in this course, we're just going to run the Yara rule through Yara.exe and view the results. If this were production and we were using this in real life, we would probably want to go ahead and compile those rules. So depending upon your preferences, you can add Yara to your path just to make it easy to call. We've done that, and it makes it a little bit easier when you're working in the lab to be able to issue a call out to Yara and have it run and not have to be path conscious of where it's at. So this is the setup. This is the Yara that we're going to be using in the course, the Windows variation of it, this 64-bit. Everything should still work with 32-bit or other versions, even though it may not have been fully tested there. If you want to stick one-to-one for the course, this is what we're going to be using. So we know what Yara is now. We know where to get a copy of it. Let's go ahead and start using it and learning about how we can use this tool to benefit our threat hunting and our malware analysis. If you've enrolled in this course, it is very likely that you already know how to write a rule in Yara. However, if you're a little rusty on it or you have a little bit of an experience gap with that, we're going to run through very quickly what a Yara rule looks like. That way, everybody is starting from at least a common point of reference when we talk about the different elements that make up a rule. You can see the code section that we have here. This is just a very basic outline shell of what a Yara rule should look like. If you notice the /* symbols at the very top on lines 1 and 3, they are used to designate a comment. You can see that we've commented this as a Yara rule. It can be the /* or it can also be a double slash if you just want to add a single comment line. Line 4 is really where the rule starts to take shape. This is where we define the rule, we give it a name, we give it a tag, and we give it that opening brace. Now the tag is optional, it just helps with searching. The key here is that you want to designate a rule followed by a name for that particular signature or rule that we're writing. The opening brace can be on that line or it can be on the line following. Either way is correct from a syntax standpoint. Line 5 starts the metadata definition for the rule. This is sort of some high-level information about the rule itself. Line 9 sets up the section for handling the definition of our string values. And then line 12 defines the condition on which a rule should be considered a match. Now, if we step a little bit deeper into this and just look at the metadata section of the rule, you can see that it's essentially name value pairs. And this is a pattern that's really going to follow through metadata and also the strings, like a series of name value pairs. The meta section does not contain any rule logic itself. This is just information about the rule itself for classification, for searching, for identification, and so forth. And there's really no required set of metadata. You can add whatever you feel appropriate here. Typically, you see the author of the rule, a description of the rule, version information, last update, and in some cases even a hash value, so that you can prove out the integrity of the rule and make sure that it has not been manipulated. The strings section is the area in which we define a series of name value pairs that represent the patterns or the indicators of compromise that we're looking for. Malware typically contains some unique and interesting strings, and these are ideal for building your Yara rule around looking for these string references. When you set up a rule in Yara, the string needs to be declared as a variable. We'll do $S1 equals myString as a very basic example. That would be search string number 1, and we have a value associated with it. You can also add certain modifiers that affect the matching of the string when it's being evaluated. These modifiers can be full word if you want to match against an exact complete word. It can be no case if you want to match regardless of the capitalization or lack of. And you can also use wide ASCII in order to match on ASCII and Unicode characters both. So you can see how adding these modifiers can affect the outcome of your match. And that outcome is determined by the condition. This is the processing logic, so to speak. It's all done in the condition segment of the rule, and the better you are at writing conditions, the more efficient you are at writing conditions, the more valuable your rule will be, the more accurate it will be, and it will help cut down on some of the false positives. So the condition is just a logical statement. If you just want to match on the first string defined, the example is what we have here, where you just do a condition $S1. If you want to match on S1 and S2, the syntax is $S1 and $S2. It's very readable, very transparent in its logic. You can also apply a match condition against all of the strings that you have defined. That's designated by a condition of all of them, or any of them if you just want to be able to hit one of a number of various strings that you have defined. Any one of those will trigger a match. You can also do some more advanced condition processing here, where you can specify a file size. For example, file size less than 1 meg. That is a default processing condition within Yara, and it will compare the file size that it's operating on against that condition. You can also inspect a file for its type, and we'll get into this in more detail later in the course, but you can determine exactly the type of file that you're working with regardless of the extension. We've got an example of that here where we define out a condition where our S1 equals inside the braces 4D5A, and it matches at the 0 position within the file. That's just another example of how you can set a condition to operate within your rule. So just a quick refresher on your rules, or perhaps a very quick introduction to them. You will become much more familiar with these as we work through the rest of the course. All of the rules follow a very similar pattern where we set up the rule name, we give it some metadata, we give it strings to match on, and then we build out that logical condition. Very similar to what you see here. As always, these are your rules. We're using them as examples, a way of illustrating concepts and teaching here. In the real world, you will probably want to combine some of these, and that is up to you in your environment and how you want to take these rules and move forward with them. A standardized naming convention can really help authoring and writing rules much easier and much easier to understand when you have to share these rules between multiple individuals, or even remember later on why you wrote a certain rule. You may want to consider using a standardized naming convention. And we've got one that you can use in the table that we have listed here. And in most cases throughout this course, the conventions that we have here are the ones that we're going to work with. There may be some deviations, especially if it helps us convey information, make the material easier to consume. We may deviate from these standard conventions from time to time, but by and large, this is the naming convention that we're going to use for our strings. We will use a variable of A to represent an application. And a good example of that would be the servicecontroller.exe. You can see that on the first line. We have $A1 equals sc.exe. That's a good example of identifying an application as a string value that we want to search for a reference to. The variable C will be used to represent a command. The variable F will represent a file. And in this case, we've got wsoc32.dll. The difference between the application and the file would be that an application is executable in some form. A file is not. A DLL may contain commands that are referenced, but it's not necessarily executable as a .exe would be. IP will be used to represent IP addresses. P will be used to represent a running process. The letter R is used to represent a reference to the registry location. And then S, we've seen this before, it's just a generic string. So use this as sort of a guide, adjust it to fit your own needs, and understand as we work our way through the course, this is probably the naming conventions that you will see over and over again throughout the course in the different lessons. The only way that we would deviate from this would be if it helps make the material easier to understand or present. In this lesson, we will help get you started using Yara against a static test file. This is one of the easiest ways to test your Yara rules. It is very basic, it's very simplistic, but this is the approach that we'll start with, and we'll build from here, showing you some additional variations in future lessons. The easiest way is to take Notepad, embed the strings inside a text file that you want to search for. And these would be the strings that are also embedded inside of your Yara rules. That way you can run your Yara tool against this particular text file and see the results. You can see here that we've got a test file where we've embedded some different references to DLLs, different commands that may be part of those DLL files, and we save that out to ytest.txt. Then we run a Yara rule against that in step 3. We issue the Yara command followed by the -s-m. -s tells us to show the strings, -m says show the metadata according to that rule. And then we're looking for content that's inside our network_udp.yara file. We'll get into that file later on in detail. But for right now, just know that it contains a series of files and commands used to set up a UDP network connection. So that's our rule, and then we point it at that ytest.txt file. You can see here when we run it, we get the results that we're looking for. We searched that particular text file for all of the strings that were encoded inside of our Yara rule, and you can see in the console, we've got the file location of where they're embedded inside that text file. It finds all of the file references. It also finds all of the command string references. Prints it to the screen. That was the -s. The -m shows you at the very top the metadata around this particular rule, the description, and so forth. So this is one of the most basic ways that you can go about testing a Yara rule, is just simply to run it against a static text file that contains the content that you're looking for. Of course, a negative test would be to execute your rule against a text file that does not contain any of those strings. That way you can do both positive and negative testing of it. One very common approach for supplying Yara with data to run and apply its rules against is to use a tool called strings to extract string values from an executable or binary file. The point is that it's a static file that you would be extracting these string values from. The strings utility is freely available. It is produced by sysinternals, and the purpose of this tool is to extract strings from binary files. The syntax is very straightforward. In this case, we're demonstrating how you can use the 64-bit variation, strings 64, against ytest.exe. And as you can see, when strings runs, it starts to return back various string values that it's discovered inside that executable. We run down the list. We give you several examples here where you can start to see the volume of information that you can potentially pull out of a binary. And this makes it an excellent way to obtain these string values and provide that as a source for your Yara rule to run against. The way in which you would approach this, the pattern would be to execute string 64 against a static file in order to retrieve those values. Typically, you would want to redirect this to an output file. That way, you can run Yara against that output file. that text file that you've saved. And you'll see this demonstrated sometimes through this course. We're going to use multiple different approaches because in some cases we want to be able to demonstrate against a static file. In other cases we want to be able to demonstrate against a dynamic file or even a process that is running in memory. However, using string 64 is a valid approach. It's a very common approach that you'll see out there in the industry. It's a very easy, convenient way to source all of those string values, export them to a file, and then run Yara against it. Another testing approach to consider is to build a static executable test file. And in this example, we will build a test file that has a number of strings already embedded inside it. The concept is that this would represent the file that you are inspecting with Yara. It is the file that will be the target of your rules and your conditional processing. In this example, we've got ytest.exe. You can see as we run this particular executable file, it's got a series of embedded strings, all of them related to the WinSock libraries. We've got it running with a process ID of 26216, and it's ready for a rule testing. That's when we execute our Yara rule for network_udp.yara rule and point it at process ID 2616. At that point, you will be able to detect whether any of these strings are embedded inside the URL that is running with that particular process ID. The way in which we construct this is using a C# executable. Lines 1 through 6 import all of the required libraries, and then lines 14 and 15 provide the information on the text executable and the trigger strings. This is all done through a series of console.writeLine commands where we indicate that it's a file for Yara testing, and we indicate that we are going to present a list of the trigger strings. Line 17 through 28 is where we actually build that list of strings that are embedded inside the test application. So we've got a reference here to each one of the WinSock DLL, system.net, and the commands send to, receive from, and so forth. These are all of the files and the commands that are related to setting up that UDP communication. They are embedded directly inside a list inside of our C# application. Now, to wrap this up, we have a loop on line 30, and that's going to iterate through that list of strings and display them for the user. The way in which we get the process ID from our ytest.exe is handled on lines 35 through 39. And the whole purpose of this is to let the user know the process ID that you need to point your Yara command to. You can see here that we get a collection of processes, and we cycle through those processes looking for the particular process ID associated with our application, ytest. Finally, lines 40 and 41 let the user know that they can start their rule testing. And then we pause for that testing, and when the enter key is pressed, the application ends. So this is just another technique that you can use if you want to embed your strings directly inside a test file. This is very good for positive and negative testing both. You should typically have a library built of different test files and different test scenarios. That way you can prove out the effectiveness of your rule before deploying it into production. In our final example of producing test files, we will talk about how to build a dynamic executable test file. Now, what makes this dynamic is that as our test file runs, it will actually pull in a list from an external file of the different string values that will be embedded inside it. You can see in this diagram here that we have ytest.exe. It pulls input from a standard text file, embeds those strings inside the application itself as it's running, and then we can use Yara in order to inspect that running process. You can see here that we've got an example where the test file is running with a process ID of 26216, and it's got all of those references to the WinSock DLL, system.net, and so forth. And then we've got our Yara file that is applying a rule to it, and it's being handed the 26216 process ID as the target ID in order to inspect. So this is a way that you can have one test harness that runs that pulls in data from an external file and uses those as those search strings that you're trying to pattern match against. Now, the way in which we build our test file is with C#. And if we look at lines 1 through 7, this is just where we import all of the required libraries. Line 15 and 16 give us information on the test executable itself and the trigger strings, just some user feedback there. On line 18, we set up a try block where we read the content of ytest.txt file. That's the file that makes up our trigger list. That's our list of strings. Once we have that in place and we read that file, we read all the lines in, and then we loop through each one of those lines. We've got that on 23 through 26, and that's where we provide feedback to the user, listing out all of those string values. Any failure, like if we can't find our list of strings, is handled by the catch block on line 28. We get the process ID, or the PID, of ytest.exe, and then display that on the console. That's all done on lines 36 through 40, and the reason that we do that is to let the user know the PID that should be referenced in their Yara command line. Finally, on lines 41 and 42, we let the user know that they can start their rule testing, and when the enter key is pressed, then the application will end. We've got two different screen captures here. The first one is what happens when we don't have that ytest.txt file. That's the missing file that the catch block handles for us. It tells us that there was an error getting the trigger list. Make sure that we have ytest.txt in the current working directory. The second screen capture here illustrates a successful run. This is our ytest.exe running. It pulls in all those string values from the resource file, and then it communicates back to us the process ID, in this case 35624, and it waits for us to do our testing and hit that enter key. So that's a depiction of a successful run. When we actually run this, you can see that we run in the first screen capture, the ytest.exe, we've got a process ID of 17020, and we've got a series of strings that we've pulled in. Now when we run our Yara rule against that, you can see that we start having matches. We start iterating through that list, matching and triggering on those found values. So this is a way that you can construct a reusable test harness that pulls in string values from an external text resource file, and then illustrates how you can get the process ID of that process running and point Yara at it in order to inspect for those values. This portion of the course is going to be dedicated to learning how we can use Yara to identify file types and inspect the content of files. This lesson covers a variety of different situations and use cases, and it's presented cookbook style, same as the rest of the sections in this course. And we're going to focus on how we can use Yara to identify the type of file that we're inspecting and also look at the content. And this would obviously be done under different contexts. One of the things that you want to keep in mind is that attackers can try to trick you. They can try to mislead you by changing the extension on a file. You can change an exe file to a .txt file, and it looks much less suspicious, much less harmful than it would if you thought it was something that would be executable. However, those files can still retain their ability to execute and run. Yara can use something called the magic number in order to look at a file and determine the file type, even if the extension has been changed. So we're going to do a pretty deep dive into that, and we're going to look at how we can use Yara to determine if a file is an executable, if it's a PDF, if it's a JPEG, and so forth. Now, from a pattern matching standpoint, there are a couple of components here that we're going to touch on. Matching on trigger strings and also matching on code references. When we apply this approach to using Yara for threat detection and malware analysis, what we're doing is we are looking for any type of embedded strings that may be of interest. This could be content in log files. It could be content that has wording or phrases that seem out of place. Imagine if you were inspecting a file that was produced by one of your development teams and you saw the string backdoor. That might be something that would trigger your interest, and you would want a Yara rule file to trigger and fire if it sees that type of content match within a file. Another aspect of this would be the code detection, where we're matching on code references. This would be if we see a string inside of a file that makes a reference to calling another component, another command, issuing some type of coding instruction, we would want to be able to trigger off of this because it may be a threat to us. It may be a piece of malware that we're inspecting. So for this lesson, we're going to look at the file structure in terms of magic numbers, code detection to pick up on embedded commands, and also trigger strings in order to identify values of interest. One area that Yara is incredibly helpful with is being able to determine the true type and nature of a target file. Oftentimes, bad actors will attempt to hide or disguise their intentions by taking an executable file and renaming it to something much less suspicious, something much more benign like a .txt file. They do this in the hopes that they will be able to pass this file along and it will slip through our defenses because we think that it's a safe .txt file and not an exe file that could contain malicious payload. Embedded within every file is something called a magic number. This magic number is just the first few bytes of a file, and its content is unique to different types of files. So we can build Yara rules to look for different patterns in these first few bytes that make up the magic number. And that's what we're going to leverage for determining whether a file is an executable or not. Every executable has the values 4D and 5A in the file's 0 position. Based on this, we can use Yara to inspect those first few values and to determine whether a file is in fact an executable or not, irregardless of how it's been renamed. The rules that we have here show two different ways of doing this. The first rule looks for the 4D5A value. You can see that we set it up as a string to search for in line 6, and the condition is we're looking for that particular string value at the 0 position within the target file. If this is in fact embedded within the target file at the 0 position, we will have a match indicating that no matter what the file has been renamed to, it's still an executable file. It can still run and deliver its payload. The second method is very similar, but there are a couple of subtle differences here. Notice we have no string values declared. We simply have a rule, a metadata statement around the description, and then we have a condition. That condition references an unsigned integer 16 at the 0 position. And then we have the hex 5A4D. This is equivalent to the previous rule. It's just looking at that 0 position location for that value. They're functionally equivalent. They do the same thing, just two different ways of writing that particular rule. You can see here when we run both of our rules in the lab environment, when we run the first rule against an executable file, we come back with a positive scenario. When we run that rule against a text file, we come back with no matches found. The same for the second variation of that rule. We run it against an executable, we have a match. We run it against a text file, we have no match. So this is just a demonstration of two different ways in which you can verify and prove that a file is in fact an executable and not something else. Again, using the magic number, we will inspect a file in order to determine if it really is a JPEG image file or not. So the magic number for a JPEG is FFD8. That is located in the 0 position of the header. So much like the other example that we've looked at, you can set up a basic Yara rule that identifies FFD8 as being the search string, and then the condition is that search string at the 0 position. If that is a match, then we'll have a trigger, and we'll know that the file that we're inspecting is in fact a JPEG file. This comes in handy when you're trying to look at potentially files that have been uploaded to your application, and you want to make sure that your users are truly uploading JPEG image files and not an executable or some other type of file that has been renamed to a JPEG. That would be an indication of some type of malicious activity, somebody trying to work outside the bounds of your application. So again, it's just that search string at the 0 position. FFD8 will indicate a JPEG file. And let's do one more magic number example here. In this case, it would be targeted at PDF documents, PDF files. And one common use case here would be uploading PDF files, perhaps to an application. You may want to have the capability to move them to another location outside of your application, scan them, detect whether you actually have a PDF file on your hands or not, and then act appropriately. So we're going to look at the magic number one more time. The magic number that we're looking for is 25, 50, 44, 46. Now, why is that the magic number for a PDF file? Well, that's obviously a hexadecimal value, but that corresponds to the ASCII value of %PDF, and that's what's embedded in that 0 position. So we're going to use the same rule structure. We're going to set a string to equal that value, 25, 50, 44, 46, and then the condition is going to be a match at the 0 position. Go ahead and test this out in your lab. Try running this against PDF files. Try running this against non-PDF files. Try altering the extension of files in your lab and running this rule against it. You should get the results that you're looking for just based upon that magic number lookup. One way of using Yara is using it as a broad, sweeping type of search program in order to pick up on what you would consider to be suspicious strings within a file. These suspicious strings, they could be strings like backdoor or virus, hack, exploit, things that might not be right. There's going to be certain values that just seem to suggest that things aren't correct. Maybe there's a legitimate reason for some of these values, these words and phrases, to be in a file. Other times it may act as an indication of something malicious or just something unwanted, perhaps a backdoor that was embedded by a developer. So we're going to build a simple search string based set of phrases and words that may be pointers or references to things that are unwanted. So any words or phrases that you would associate with behaviors that are out of bounds, out of line with your environment may be valid strings for this type of rule, and you can go ahead and embellish this, add to it, extend it, do what you need to do in order to customize this particular rule to better fit your environment and your situations. So the string that we have here indicates backdoor, virus, hack, and exploit as different patterns that we will match on. The condition that we have within the rule is any of them, so we're looking for any one of those hits. You may want to adjust this in order to tighten up that condition a little bit, maybe picking 2 of them, 3 of them, especially as you extend your list and you expand the search strings that you're looking for. Notice we do have no case ASCII wide as modifiers for each of these strings, and you can see that when we do run our Yara rule against a test process, you can see that it does pick up on all of those different variations. So consider those modifiers as you build your rule. We're going to look for every variation of those strings as we pass through. That may be overkill in your environment. Maybe you want to slim that down. Maybe you want to keep it just the way that it is in order to get that broader range of coverage. So a fairly generic rule, but one that is powerful in the sense that if you spend some time developing your list of suspicious strings, it could be very beneficial for you as one of those wide sweeping searches that you do across a set of files, perhaps, in order to try to minimize the number of files that you got to dig deeper into. Sensitive data is often personal identifiable information or personal health information or even personal financial information. These are all sensitive data values that you may collect on your customers that you want to protect. You want to keep it private. You want to be able to avoid breaches in your data security because there's often significant regulatory consequences when these types of breaches happen. Obviously, this type of data is a key target for malware. Yara can be used to help us in these situations because we can scan files for signs that there may be embedded content or instructions in those files to search for PII and PHI. We can also use it to search files that are being exported out of our organization in order to determine if they may potentially have sensitive data. So the rule that we're going to write in this lesson is built around looking for several different values that are categorized as personally identifiable information or personal health information. We're going to use regular expressions to help us search for these values because what we're really looking for is a structure and a sequence of values rather than the actual content itself. If the content matches this structure, then we have a pretty strong indication that we may be working with sensitive data. What we're going to look for would be social security numbers and credit card numbers, and we're also going to look for healthcare identification numbers and diagnosis codes, the ICD-9 and 10 variations. These are all common values that you find in different organizations that process personal information or health information, and this will give you a good starting point for building out your rule set in order to identify this type of data. The rule that we have is pretty straightforward. We've got 2 sets of patterns identified in lines 11 through 15. The first 2 are PII patterns, lines 11 and 12. The first pattern is set up in order to trigger on social security number. So the regular expression defines 0 through 9 and 3 digits. That's the first part of the SSN, followed by a dash. Then we repeat 0 through 9 as digits for 2 positions, followed by a dash. And then we've got 4 positions of 0 through 9. If we inspect line 12 of our rule, you can see that it's a very similar type of structure, only we vary this in order to match the pattern associated with a credit card. Obviously, there are all numbers, 0 through 9, and there are 4 sets of them split by the dash symbol. On lines 13, 14, and 15, we start with our PHI identifications. The healthcare identification number is an 8-digit number, and it can contain alphanumeric characters as well. You see that defined in line 13. Line 14 is the diagnosis code following the ICD-9 pattern. This is a set of 3 digits followed by a dot followed by 0 to 2 digits. The ICD-10 variation of this is shown on line 15, and that regular expression is very similar, but it includes alphanumeric characters on the first half of the designator, 2 positions there followed by a dot, and then 1 to 4 digits following. The condition that we have set on lines 17 and 18 would be a match on any one of these patterns. Now, these are just basic patterns. You might need to refine them, expand them. Be cautious. False positives could happen here, so you want to make certain that you've got legitimate strings and you do testing, both positive and negative. When it comes to testing, we've set up a static file. It contains a number of different variations that may or may not match these patterns that we have defined in our Yara rule. We go ahead and execute the Yara rule, and notice this time we also add the -w parameter to our command line. This will suppress warnings. The reason that we've done that is we have not compiled these regular expression values. Therefore, the Yara tool will give us a warning that says that you could potentially increase the speed and the efficiency of your searches if you compile the rules. In a real-world scenario, yes, we would compile those. That way we get those performance gains. But just for this demonstration, we'll suppress those warnings with a -w. We will run against our ytest.txt file, and you can see that we start to have matches for the various different patterns that we have defined. Threats can come in a lot of different forms and from a lot of different sources. And one of these sources of a threat could be the production release of vulnerable source code. Now, nobody is saying that a Yara search would ever take the place of security code reviews and security testing, but sometimes you can use Yara in code crawling exercises. These are exercises that are designed to highlight areas of source code that might require deeper inspection. We can certainly leverage Yara's pattern matching ability in this area. And the rule that we're going to build here is fairly generic in some ways. We're looking for certain types of patterns, whether that's a weak TLS cipher pattern or an insecure cryptographic pattern, or maybe some patterns that deal with SQL injection and cross-site scripting. This is an example. We expect you to take this, build on it, customize it for your environment, looking for specific strings related to the languages that you use in your application development. There are a couple of differences with this Yara file. We are going to build one .yara file that contains multiple rules. Now, this breaks with a pattern that we've had throughout this course, but we've done it this way so that we can condense several types of patterns into one file, and we can also demonstrate that this is a valid use of Yara and a valid way to build your Yara rule files. So we're going to write this one single rule, and for the sake of brevity and cutting down on the amount of code that we have to walk through, we're going to eliminate the meta tag for this. A little bit of a difference from what we've seen in some of the other lessons, but that is a valid approach. And one of the other things that we are going to do is we're going to break from our naming convention a little bit, and you'll see the search strings here in this next example will be a little bit more elaborate in terms of the naming of each one of those search strings. We're going to be a little bit more descriptive just because it helps relay the information a little bit better. So this rule is going to cover a wide range of security issues. There's going to be multiple rules contained inside a single file, and you always want to make sure that you take this as a basis to start from, customize it, stay up to date with the latest security practices for whatever language it is that you use to write your application code. So line 4 of our example illustrates how we can set up a detection mechanism for weak cipher patterns. SSL v2, the SSL RSA with DES, CBC, SHA, those are weak ciphers. They have been replaced, and if you see a reference to this in your code, you might want to look deeper. The condition for this particular rule would be to trigger on any of those strings. And that's really the same pattern that we're going to follow when we talk about insecure cryptographic patterns. MD5 and DES, they've both been deprecated. We've got stronger cryptographic functions out there now, but our rule will pick up on these matches and trigger against either one of them. Obviously, there are more insecure cryptographic patterns out there other than MD5 and DES. That's research that you can do on your own and add to this rule, enhance it. Depending on the languages that you use, C and C++ code, that's known to be very vulnerable in terms of the gets and the scanf functions. These two functions take input from the user. That's input from outside of your application. And we know that whenever we're receiving input into our application, we have to treat it as untrusted until it can be validated. So from a code crawling perspective, you may want to highlight in your code, automatically find in your code where there are references to either one of these functions. That way you can dig deeper into it. Again, customize for the languages that you use in your environment. The last three patterns here deal with path traversal, cross-site scripting, and SQL injection. Not in terms of finding out whether you've been attacked, but rather, is your code set up in a way that predisposes you to an attack? For example, in the path traversal pattern, we've got two different search strings here on line 30 and 31, and they make use of the ... notation for moving between folders, files, and locations on the file system. You know, whenever you have these shortcut references like this, these relative paths, then you potentially have an opening there that your application could be manipulated from a path traversal perspective. So you want to know about these potential weaknesses. The same is true for cross-site scripting. In a lot of cases, cross-site scripting will attempt to manipulate source code that makes use of a script tag or document.cookie. There are a few others. Image tags and so forth can also be included here. So if you're inspecting quickly in an automated fashion source code, you may want to highlight on different lines that contain these types of references. And the same can really be said about the SQL injection example that we have here. Select star from and union select are both two SQL query statements or fragments of a statement that deal with building dynamic queries, and they are often subject to SQL injection attacks. So if you find these in your code, you might want to take a second look at it. Again, all of these are set to trigger against any of them. And finally, in our lab, we have a static file that contains all of the search strings, and we have our Yara rule file that is actually made up of a number of different subrules. And you can see that we execute that against our test file, and we start making hits on these different string values. While Yara is not typically considered to be a log management or log searching tool, because certain log files are written out in text, you can use Yara against a log file looking for certain patterns. And that's what we're going to do in this lesson with an IIS log file. This is the Microsoft Internet Information Server. It's a web server that is common on the Microsoft platform. And because these types of system logs are made up and stored as text, you can use Yara for a quick inspection of the content, a very lightweight searching. And this lesson is going to use a simplified example of an IIS log. The log is configurable in terms of what fields you want to have captured. So every environment is going to be a little bit different. So it's a simplified, cut down version of it. And each line is going to represent an entry in the log. The header captures information such as the date and the time, the source IP address, client IP address, information around the URL that was requested, the query string, the response number, and so forth. So all of these are values that are captured in that log that you could search upon. And there are a lot of different scenarios why you would want to search an IIS log file. In the example that we're going to work with, we're going to target a specific page request, in this case logon.aspx. The string that we defined for the search here is, again, just an example of searching for a single page. Why would we show it in the context of a course dedicated to malware analysis and threat detection? Well, think about how you could use this to your advantage. Suppose you set up a honey page, a page that was restricted from crawling by your robots.txt file, set it as a deny. Search engines that are going to respect that will not crawl it. However, somebody looking to inspect and get an inventory of your web application and website may actually crawl this page, request it, and that would show up in the logs. So this is why you would potentially want to have a Yara rule that would search for the presence of a request against a certain page. So the condition here is set to look for any of the defined strings. We only have one in this example, but the thought is that you would add to this. This would be a setup for you, a starting point, and then you would add more pages to be searched and triggered upon. Examine the header of the log file and think about all those different fields. There are a lot of different scenarios that those fields would play into from a threat detection standpoint. You could use it to identify certain HTTP methods that you want to be aware of. Maybe look for a specific IP address or search the values inside query strings for certain patterns. Of course, you can also use it to look for various user agents. So there's a lot of possibilities here using just a very basic Yara script that's built around string matching in an IIS log file. Here's the example. We look for the logon.espx page. That's what our Yara rule is defined to search for. And we get a trigger. There is a request for that particular page within the example log file. So a very basic script, but one that is very much extendable and can be used in a lot of different ways in terms of looking at your IIS logs for certain values that might be part of your threat hunting and threat detection efforts. In this lesson, we are going to talk about how we can use Yara as a very lightweight preprocessor to Apache log files. The scenario that we're going to talk about that really sets up this lesson would be one where we have a website that we're operating that works under the HTTPS protocol. Obviously, we would be using this for security reasons in order to encrypt that data exchange during the transit between client and server. So if a request is made for HTTP, we've got a couple of different situations on our hands. One, it could be a request that is issued that we will respond to, and that would represent a security misconfiguration that we would want to correct. Or it could be an HTTP request that is made in order to probe our website and see whether we'll respond to that. So it could be an indication of a misconfiguration, or it could be an indication of somebody doing recon against our web application. So we're going to take a fairly standard Apache log file. Just keep in mind that these log files can be adjusted to capture different types of information. So adjust this to fit your environment. But we'll be looking at that standard log file that captures things like client IP address, the request method made, the URI, protocol version and response, and so forth. So we'll be dealing with some of those standard fields. The rule that we build is, again, just based on search string pattern matching. The Apache web server file is a text-based structure, so that makes it very convenient for Yara inspection. We'll run through this. We'll set up the search string on line number 10. That's where we designate it as HTTP:, and the rule we just have set as any of them, and that's based on the fact that you could take this structure and repurpose it, reuse it, enhance it, looking for any of those other fields within the HTTP web server log file. Some of those other fields that you may want to consider would be identifying the HTTP methods used, searching for values within the query string, or even looking for various user agents. But for now, we'll stick with just searching for HTTP. You can see here we've got an Apache web server file. It's got a number of different transactions in it. You can see just visually a lot of them represent HTTPS. You can see that middle transaction, however, does reference HTTP. So when we run our Yara file against that, the rule matches and it triggers on that particular line that has the HTTP reference for us. So this is just one technique that you can use if you have a scenario like what we've described and you want to do a little bit of log preprocessing looking for certain conditions. Let's spend a few minutes talking about how we can use Yara to inspect FTP server transaction logs. As we said, we would never really replace a fully functioning log management system with Yara, but you can use it as a lightweight preprocessor to scan server logs prior to ingestion by a downstream system. And that's what we're going to talk about with this particular lesson. We are going to build a Yara rule that can inspect an FTP server log for signs that a request has been made by a certain user. So aside from just demonstrating basic pattern matching and searching through this particular type of log, this lesson is also going to attempt to demonstrate how you can detect the use of a specific honey account. Now, one way in which organizations can detect actual or attempted compromise is through something called a honey account. These accounts are often non-functional and they're used as decoys only. The purpose is that if the account shows up in a log file, then it's an indication that somebody's attempting some type of unauthorized activity. So this is an alerting, a detection type of capability that many organizations use. The example FTP traffic that we've captured here shows two different users, user 1 and user 2. The user 2 account is the honey account in this particular example. And you'll see that each one of the users has a number of different commands that they issue. User, pass, PWD for print working directory, CWD for change working directory. They've got a retrieval of a file, and then a quit of the FTP session. So there's some traffic generated by each one of these users in the example file. The rule that we have here is just a basic shell. And remember, pattern matching and searching is oftentimes the easy part. The difficult part is knowing what to look for and why, and how to do this under the context of achieving a certain objective. So in this lesson, user 2 is the honey account. If this user shows up in our FTP log, then it indicates that somebody that's obtained the account is attempting some type of access. The search is easy enough. Line 10 sets up the search string, and the condition is tested on line 12. The rule was intentionally left open-ended and somewhat vague. The condition was set to any of them. Now, this was done in anticipation that the rule would act as a starting point for additional extension and customization. Take this, adjust it as you see fit. One suggestion would be to examine the header of the log file and think about the different scenarios and use cases that this might fit with a rule of this nature. Start to identify FTP commands that are used. Use it to target a specific client IP address. Search for certain files that might be retrieved. That would be an example of a honey file, perhaps. And look for various movements as the user works their way through the directory structure using the cdw command. From a testing perspective, we've got a static log file, and then we run our FTP_log Yara rule against it. This is the rule that we defined on the previous slide, and you can see that it has in fact picked up references to user 2. Network reconnaissance, or network recon. You hear about this a lot of times in different courses, and a lot of times you hear it related to things like the penetration testing process and so forth. But there is also an element of recon with malware. Many times, once malware has been deployed, it will start a reconnaissance effort. It's going to try to look around, determine where it's located, the access that it has on the system that it's been installed to, and what other targets might be available. And that's what this lesson is going to be built around. We're going to use Yara to inspect processes and files for signs that they might be capable of performing network recon. Obviously, this is something that you want to key in on and dig a little deeper into in order to determine if these types of networking commands that might be embedded in a file or process are truly just network commands, or are they being used for something more nefarious. Other times, you want to look at a process or a file and try to determine if it implements things like packet capture capabilities. All of these elements come into play when you start to think about network reconnaissance. From a pattern standpoint, we are going to be looking for two things. Trigger strings, being strings of value or interest that play into this particular context, or code level detection for embedded commands. Let's go ahead and get started. There are a number of different services and websites on the internet that will tell you what your external IP address is. So why is this important? Well, oftentimes malware will take control of a system and then it will try to figure out what that organization's outbound IP address is. That way it can recon the network and it can understand where the malware is deployed, what the organization is, and provide this information back to the attacker. So we need to be able to inspect a file and figure out whether this type of capability may potentially be built into it. So we're going to construct a Yara rule that is going to look for a few of these IP address lookup sites. Whether it's check IP, what's my IP, getmyip.org, we've got a number of these that we've embedded inside the rule. Now, these are certainly not all of the lookup sites. Just a simple Google search will provide you with a series of sites that offer this type of capability. We would expect that you would take this rule as a starting point and expand upon it. So it's a pretty simple rule. We've got a number of strings set up in lines 9 through 12, and they're just references to these internet websites. Notice we have a no case modifier on it, and our condition listed on line 14 is very straightforward. We would be looking for any of them because if there's a reference with this inside a file, then it's very likely that this file will try to reach out and figure out what your organization's external IP address is. Right now, we've just got these 4 sites listed. A possible modification would be to take the DNS names of these, switch it over, and use the IP addresses of some of these sites. That might be an improvement that you would want to consider. When we run this against our static test file, you can see that we've embedded each one of the URLs, and we do pick up on them with the Yara test rule. Make sure that you do positive and negative testing, but this is an indication that we are able to trigger on these different types of URL references. Being able to pick up and capture packets across the wire is an incredibly useful ability for an attacker to have. One way that attackers use this capability is to build malware that has packet capture aspects to it built into the code. Capturing these packets, the attackers can collect them and analyze them on the fly. They could store them, analyze them later. You can inspect this network traffic. Even if it's not encrypted, you can pull out IP addresses, hosts. There's a lot of information that can be gained by analyzing captured packets. So in this lesson, we're going to talk about how we can determine if a file has this type of capability built into it. Now, packet capture can be accomplished in a lot of different ways. Two common elements of packet capture typically centers on utilization of a driver to interface with a network adapter and another component to interface between the driver and the OS or the application. In Windows, the npfsys and packet.dll provide this type of capability. If you want to use something a little bit different from what's provided with the base operating system, you want a third-party element to this, then you can use non-OS supplied drivers and interfaces like WinPCAP. This is a third-party implementation. It's very similar to what you see in Linux implementations with PCAP, libpcap. A very popular tool is TCP dump. All of these are packet capture sniffer type capabilities that are added through these types of files. So within our Yara rule, what we're going to build is a lookup against packet DLL and npf.sys. This would be your Windows components. And then we're going to look at wpcap.dll and winpcap.dll. That would be the third-party capture and driver components. The rule contains matching logic that's going to be based on these references. The strings section lists all four of these, the packet, npf, wpcap, and winpcap DLLs. And what we're going to do initially is a compound condition. On line 14, we're going to check to see if we're working with an executable file. This is the magic number that we looked at earlier. And then we're going to combine that with an AND condition. Should it be an executable file and any of the string values match, then we trigger. Now, a revision that you could make would be to remove the requirement for an EXE, which would be stripping out line 14 and replacing it with a condition, any of them. Notice we've also dropped the AND off of that, just simply because this is a singular condition at this point. So, if the rule's used as is, both conditions have to be met. If we modify it and we remove the EXE check, then the condition is simply any of them. Here within our lab, we have mocked up a static text file that contains the references to the packet capture DLL and system files. We've also executed our Yara rule against that particular file, and you can see that we have matches. Obviously, we've run the variation of this that has the any of them condition and does not have that compound condition that looks for the presence of an executable file as well, just because this is a static file in Notepad that we're running it against. So we've left that condition out of our test run. Test this in a variety of different ways, positive, negative testing, and also testing with the embedded check for the magic number on the executable. In this lesson, we're going to take a look at some common Windows networking commands from the perspective of living off the land. Have you ever heard of this term before? Do you know what living off the land means? Well, it's a concept that comes from attackers and red teams that involves leveraging tools that are common to the operating system. That way, you don't have to load those tools onto a target system. It helps you stay low profile, fly under the radar, and not attract too much attention to yourself. So in this lesson, we're going to focus on the network reconnaissance side of things, building a Yara rule that will help us look for the usage or the reference of certain internal operating system and tool commands that come with the Windows platform. So what we're going to look for will be ping, path ping, and traceroute, references to NSLookup, netstat, and route print. That's going to form the basis of the rule that we're going to write for this particular lesson. Now, if you notice, we're going to embed a number of different command strings. You can see them listed here in the sample rule file. All of them have the no case modifier applied to them. That way, it will be case independent when the rule is executed. Now, the first three commands, command 1 through 3, are all very similar. They're about discovery. You have the ping, path ping, and traceroute commands here. Ping is used to determine if a target host is up on the network and responding. Now, path ping and traceroute both accomplish a very similar task, but they will also show each hop in the network tracing from source to destination, perhaps back, every step along the way, showing you every single network hop or every single host that is in the middle of point A and point B, between that source and that destination. It'll show you the entire pathway. Those three are kind of grouped together because they all function in a similar manner and have a similar purpose and outcome. But NSLookup is a little bit different. That's on line 12. This is used to perform name resolution in DNS lookups. Very helpful from a Recon perspective. Line 13 is a reference to the netstat tool. This command is used to show the local system's network connections, and it can show you TCP connections, UDP connections, and connections that are listening or in an active state. So you can gather a lot of information not only about the local system and the ports that are open in the communication pathways, but also remote systems that it is talking to. Very valuable information from a Recon perspective. And then lastly, we have the route print command. This command will show the local routing table. Again, a good way of discovering your host's view of the outside world. A lot of information you can collect from that perspective. And the way in which we have our conditions set for this particular rule is to trigger on any of them. So in our lab, we embed these in a static test file and we run our win_net Yara rule against it. And you can see that we start to pick up those references to our ping, pack ping, traceroute, NS lookup, netstat, and route print. Welcome to the lesson about network communications and covert communications. These two topics kind of go hand in hand. You can have covert communication without network communications, but having the two paired together is very powerful. It's powerful because malware oftentimes needs to establish communication with the outside world. This can be a very critical piece of malware, and for two reasons. There are two driving purposes behind this. First, the malware may need to receive commands from the outside. Sometimes this is called command and control. This is where the malware will infect a system, sit there and wait for a remote operator, the attacker, to issue commands to it, which it will then carry out on that compromised system. And the second reason that there may have to be outside communication is so that any data that is stolen, files and other content, can be moved out, can be sent back to the attacker. That way they can steal your data, your information, and your content. So those are the two driving forces of why a piece of malware would want to have communication with the outside world. Now, from a pattern standpoint in this lesson, we're going to be looking at code detection and trigger strings. We're going to be looking for code level embedded commands within a file, and we're also going to be looking for strings that would seem to indicate network communication in one form or another. So let's go ahead and get started. The TCP protocol, it's the Transmission Control Protocol. It is one of the foundational protocols of the internet. And if you're looking at a process or a file and you're trying to determine its purpose and its capabilities, one thing that you want to look for would be the ability to set up a TCP socket. A TCP socket is required for communication. A socket is just simply the combination of a host, a port, and a communication protocol. TCP is that communication protocol, and it's a connection-oriented protocol in the sense that it has to go through a handshake process between communication partners in order to establish that channel. And that's very important because that's what we're going to look for in this rule. It's that three-way handshake. It's the commands that are used in order to set up and manage that connection. Now, from a defensive standpoint, you always want to manage connections in your network, and there's a lot of different ways that you can implement network level controls in order to allow only authorized communication, authorized TCP connections between hosts. But as we said, when you're evaluating an unknown process or file, you want to understand what capabilities might be there, because TCP obviously has been used and abused by malicious actors, and that's either to set up a covert channel for command and control or to move data around and steal your data and your content. Now, we said that the key aspect of TCP is that negotiation of a communication channel. And that's what we're going to target with our rule. We're going to look at the files and the commands that can be used in order to establish that connection. The WS232DLL, WSOC32DLL, and variations of those, they all contain the WinSock functionality. Those are the commands that can be used by a piece of software in order to set up that TCP communication. And that's what we're going to key in on. For our rule, we're going to define two files on line 10 and 11. These represent the WinSock files. We do have the no case modifier applied. Line 12 through 20 is where we outline those different commands that we're going to look for. It's the socket command, the send command, connect, and so forth, and the close socket to tear down the connection and the cleanup. These are all commands that are associated with building, maintaining, and tearing down that TCP session from a WinSock perspective. So the condition that we have is on line 22, and it says either one of those WinSock files and two of the commands that we have listed. So that's the combination. It's a match between one of those WinSock files and two of the commands. Now, obviously, you can vary the condition, but this is probably a good starting point for you to use. Obviously, in the lab, you want to test this out with positive and negative scenarios. You need to prove the integrity and validity of your rule. We've got each one of those items listed in a static text file, both WinSock files as well as the commands, and then we run our Yara rule against it. You can see the output here. We start making those connections. Again, test it out in your lab, prove it from a positive and negative standpoint, but this is a good starting point to be able to detect WinSock-oriented TCP connectivity capabilities within a file or process. UDP is the User Datagram Protocol. This is one of the core protocols of the Internet. It's somewhat similar to TCP in the sense that it's one of the protocols within that suite, but it's also very different. TCP is a connection-oriented protocol. UDP is not. It's called a connection-less protocol. And that's because there's no three-way handshake between the two hosts. It's got a different approach to communication, one that's centered around more of a fire and forget pattern. And based on that characteristic, the fact that it's used for very short messages that are sent quickly and don't always need a high level of guaranteed delivery, it makes it very attractive for malicious users. These bad actors are looking for ways to create these covert channels of communication, and because there's no ongoing connection, UDP looks very attractive to them. So we're going to build a Yara rule that will help us look at processes and files and determine whether they have the capability of sending UDP-based communication. And we're going to do this by looking for WinSock files in the system.net file, along with various commands that are components of those DLLs and system files. So we're going to follow this pattern of creating string references for each of the files that we want to have as part of our rule. You can see this on line 10, 11, and 12. We set up the WS232DLL, WSOC32DLL, and system.net. Keep in mind there's a difference between the two DLL files and our .NET file. The system.net is part of the .NET framework, so this is yet another way outside of pure DLLs that could be referenced or used in the creation of this communication channel. On lines 13 through 18, we have a series of commands. These are all string values, and we're going to perform a match based upon combinations of these command strings in conjunction with their associated DLL or .NET file. So it's important to look at the rule on line 20. It's sort of a compound rule. So let's decompose this and work our way through it. We have an OR condition. That means that we are going to have two possible conditions that would trigger this rule. So let's look to the left side of the OR. In this scenario, we're looking for file 1 or file 2, so that would be our WS32DLL or our WSOC32DLL, and two of our commands. So that's the first half of the condition. If we find a WS32DLL or a WinSock32DLL and two of those commands, we will trigger. Or if we move to the second half of that OR condition, or if we find system.net and specifically our C5 string UDP client, then we trigger. So it's a bit of a compound condition. It looks complex at first, but if you break it down and work your way through it, just as we did in this particular lesson, it starts to demystify it and starts to make it a little bit easier to read, understand, and see how this particular rule would function on the trigger condition. In the lab, we've set up our ytest.exe. It's got a process ID of 17020. And then we've also run our rule against it, pointing it at that particular process ID. Your process ID will look different than the one we have demonstrated here if you try to reproduce this in the lab. But we're showing positive testing. We have all of our files, the DLL and the .NET file, as well as commands, being hit with matches as this rule triggers. So, good example of positive testing against a running process. So this is just one way that you can detect the capability to establish UDP-based communications within a file or a process. There are a lot of different ways, but use this rule as a starting point. Sending messages on the internet relies upon a protocol called SMTP, the Simple Mail Transfer Protocol. When you're inspecting a file in your environment, it might be helpful to find out if it contains the capability of sending outbound mail messages. There are a number of different ways to do this. In this lesson, we're going to look at some of the raw SMT commands that can be issued. We want to make sure that if we have a file that we're looking at, it's not a file that's going to operate in a way in which it sets up some type of unknown or unwanted communication channel or has the capability of trying to move data out of our organization. So we're going to build a rule that's going to look for some of these raw SMTP commands. The ones that we're going to look for are hello and EHLO. These are two commands in the SMTP command syntax that allow you to establish a communication channel. It's the hello, the setup for sending a mail message. We're also going to look at two different commands, mail from and receipt to. This basically equates to the sender and the recipient of the mail message. So if you find some of these string references inside a file, then it may indicate that that file has the capability of dynamically building a script or issuing these types of commands to start sending SMTP communication. Here's the Yara rule. We do the basic setup with the rule name, some metadata to describe the rule, and then on lines 10 through 13, we outline those four common SMTP commands. Lines 10 and 11, those are the references to hello and EHLO. These are the hello and the extended hello commands. It gives us that SMTP communication channel setup. Line 12 and 13 are command references to the mail from and mail to commands. It's the receipt to. This is basically the setup for the sender and the receiver values for the message. Now, using these values will likely produce results for you. You may want to extend this by adding in several other command references. It would be subject, body, and quit. Subject is the equivalent to the mail message subject, and the body is the equivalent to the text-based payload of that SMTP message. Quit is sort of a control command. It tears down that SMTP session, so you may want to include that. Another consideration would be to adjust the condition. Currently we have it set to any of them. Perhaps you may want to set that condition a little bit more finely tuned and set for some number of matches rather than a broad any type match. Here in the lab as a demonstration, we've got a static text file that contains a number of different test strings. These all match our SMTP commands. And we have our Yara rule that is run against that static text file, and we see that we start to have matches on those patterns. Each one of them picks up as a hit. Remember to do your own testing and make sure you do both positive and negative testing. That way you can see the results from both perspectives and make sure that there's a level of validity and integrity to your rule. FTP is the File Transfer Protocol. This is one of the most basic ways of moving data, of moving files between one system and another. FTP is used between two different hosts. One acts as a client, the other acts as a server, and files are exchanged either through upload or download. This can happen over the internet or through your network. And finding a file inside your environment that has references to FTP commands, that might be an indication of some unwanted activity. The rule that we're going to build in this particular lesson is going to focus on detecting this type of activity by inspecting a target file for different FTP command strings. We're going to look for strings like user and pass. These are two strings, two commands that are used in the authentication process between client and server. And then we're going to look for retrieve and store. Retrieve is downloading a file and store is uploading a file. Two very common FTP commands. Now, once you have your basic rule operational, it's up, it's running, you're detecting some matches, you may want to consider expanding and fine-tuning the rule a little bit. And one area to consider would be including some additional FTP commands. Those would be commands like CWD and PWD. This is change the working directory and print working directory. Two very common FTP commands that you would see issued. List is another one. It's the equivalent of doing a directory listing. You also have delete. DELE is the command abbreviation for that, and that would remove a file. Then you have MKD and RMD. This would create, make a directory, or delete or remove a directory. And then finally you have quit. That command terminates the FTP session. So you can see how we've got a set of four very common strings, and then we have some other command strings that we could add to this if we wanted to in the future. Lines 10 through 13, they define the strings that we're going to look for on our initial pass. The user and pass for authentication, retrieve and store for upload and download. And the condition we have on line 15 is we will trigger if we find any of these matches. Again, consider fine-tuning this. Use this as an example to get you started. Consider adding in some of those additional FTP commands. And also think about adjusting the condition. Once you've pulled in some more commands, you might want to fine-tune your condition. Instead of setting it to be any of those strings, perhaps vary it for 2 or 3 of those command string matches. That might help you tune it a little bit and get a little bit more precision in this particular rule. And finally, here in our lab, we've got a static file set up with the 4 basic FTP commands. We have our Yara rule that we execute against that text file, and we see that we do in fact have a number of different matches. As always, do your own testing. Make sure that you prove out the validity of the rule in your environment, the way in which you've written it. This should be a good, solid starting point for you when building out rules to look for signs of potential FTP activity. IRC, this is the Internet Relay Chat. And back before instant message, this was how you communicated over the internet. It is one of the original internet chat protocols. It allows clients to connect to IRC servers and exchange messages and files with each other. Now, IRC is a very much dated technology, but you still see it sometimes with malicious content, and that might be done under the assumption that since the technology is considered out of date by today's standards, maybe defenses aren't properly put in place in order to control this type of communication. As the client tries to negotiate with the server to send messages to other downstream clients and have this interaction for this real-time chat, there's a number of different negotiation steps in the communication channel, and the data that is exchanged is controlled through a number of different commands that are supplied from client to server. Some of the commands are listed here. They are join, that allows you to join the conversation. Nick, short for nickname, ping, private message, and user. The rule that we're going to build looks for these commands embedded inside a file. You can see with the code that we've written here for our Yara rule, we have the standard meta tags, and then we have a listing of different strings, and these are all commands, so they're referenced C1 through C5. Join, nick, ping, private message, and user. The condition we have on this rule is all of them. You may want to modify that. You may want to remove a certain command like ping, since that can be used across multiple different types of files. Play with it, adjust your rules, tune it, see what works for you. But this is the outline of how you would develop a rule for IRC communication. When we run that, we have our Yara test file. It's got all of our strings embedded. We run our rule against it, and you can start to see where we pick up on where these commands are embedded. Obviously, it's a running process, so these are memory locations. But this is one technique that you can use to uncover files, executables, content that is trying to establish an IRC session that you don't want in place. In this lesson, we are going to cover how to build a Yara rule to potentially help in the detection of DNS stuffing techniques. DNS stuffing involves creating a number of different multiple subdomains underneath a domain. And this is done to evade detection, distribute malware content, and it's a pretty common technique that you see many times. The purpose of DNS stuffing is to hide malicious activity, evade detection, and make it more challenging to identify and block malicious traffic. They'll do this automatically. It's scripted. There's a generation, a high volume of subdomains that are dynamically created in order to build this camouflage for the malicious content or the command and control infrastructure that they're trying to hide. The rule that we're going to build here uses a regular expression to try to determine references to domains that are more than 3 subdomains level deep. You can see here that we set up our rule, give it the metadata and so forth, and then on line 9, we define a regular expression pattern. This is the key to the rule. It looks for 3 different dots to separate out those domains. That's what represents the break of the domain structure. Once we exceed 3, we start matching patterns on characters. You'll see here when we run the rule, we've got a number of different domains inside of our static test file. .com, mydomain.com, my.domain.com. None of these 3 should match. However, that last line, just.my.domain.com, should start to trigger matches. And because these regular expressions, the way we've built it, based on the number of characters after that third dot, you'll see that it starts to print out the T, the ST, UST, and just as it builds its iteration through that matching. So there's a little bit of noise here with this rule. It could be refined a little bit better, but it should give you a starting point to begin to detect when there are multiple domain references to a multiple level of subdomains within a given file. And that's one indicator that you may be working with a file that has the intention to use DNS stuffing as a camouflaging technique. This section of the course is all about how you can detect whether a file or a process contains the ability to manipulate the operating system. Being able to manipulate the operating system is a significant part of many pieces of malware specimen that we see. If you can control the behavior of the operating system, then let's face it, in a lot of cases you win. So this section is going to contain a series of lessons, and the thing that they all have in common is that they will focus on various ways malware and other threats can attempt to manipulate and take control of the operating system. And this varies. It can be through interaction with standard Windows utilities and tools. It can be altering the host file so that you can subvert the DNS lookup process. Or maybe it's to turn off different types of protection that you have on that particular host, lowering the shield, so to speak, so that more attacks and more compromise can continue. So we're going to be looking for three main things. It's going to be references to tools, calls that relate to different API interactions and libraries in order to invoke a command, or different string values that would be an indicator of compromise or an indicator of threat. So we've got all three of them at play here, looking at files, looking at codes and commands, and also looking for various trigger strings. So let's go ahead and get started. This will be a deep dive into malware and threats that manipulate the operating system. For a number of years, the Windows operating system has had a very powerful command within its toolset. That is the net command. From the command line or referenced by scripts, the Windows net command can be used to manipulate a lot of different aspects of the operating system's configuration, its users, security, and connectivity. Files that reference these commands are likely something that you want to look into much more closely, and that's what we're going to build our Yara rule around for detection of references to these types of commands. Now keep in mind, in order to execute these commands and be successful, in many cases it takes a higher level of privilege on the operating system. You may not have that initially. However, the theory is that there would be an attack in place, there would be a compromise, and that would use compromised credentials, or it would go through a process of elevating the privilege under which the account that's being used to run these commands. So keep in mind, there is an element here of access control and commands and privilege that is needed in order to run the net command, but assuming you have those privileges, then the net command would give you a way of performing all of these different network-related operations, configuration operations, and so forth. Now, the commands that we're going to look for will be the net use command. That's how you can connect or disconnect a computer from a shared resource. Net share will display the shared resources on a computer. It will also allow you to share out resources on that computer given the proper set of command parameters. Net view is going to display a list of resources, and net user is very powerful because that allows you to add users, display information about users. And then following up on that, you've got net group and net local group. These are two variations of the net command that allow you to create either groups on the local system or at a domain level. Net start and net stop will allow you to start and stop services, and net send allows you to message other users. So you can see how this is a fairly powerful set of operations that can be performed with the net command. The rule that we're going to build is displayed here. Lines 9 through 17 set up all the different commands that we're going to look for. We've added the no case modifier here, and you can see it's the same list that we talked about on the previous slide. They're all embedded here, and the condition for a trigger is any of them. Now, one modification that you may want to make to this particular rule is to add in some of the additional net commands. We've taken just a subset here. If you got to command shell and issue the command net /?, you will see the entire set of syntax and capabilities offered by the net command. You may want to add additional commands to this rule in order to improve the coverage, the effectiveness, and so forth. In the lab, we go through our standard testing process. We have our net commands embedded in a static text file. We execute our Yara rule against that, and we see the results that are displayed here. Obviously, in your environment, you want to do both positive and negative testing. You want to make sure that you have a valid rule developed and applied. Most of the time, when you need to resolve an IP address to a human-readable host name, or vice versa, DNS is used. But there's an interesting file on your operating system. It's called the host file, and entries in this host file will take precedence over DNS. On a Windows system, it's located in the Windows/32/drivers/etc folder. It maintains a list of IP addresses and corresponding host names. And during name resolution, the local host file will take precedence over a DNS lookup. So if an attacker or a piece of malware can manipulate your host file and can write to it, then they can direct traffic to a location of their choosing. Obviously, this is something that we want to pay attention to and be alerted to if a file or process attempts to reference our host file. The structure of the host file is pretty simple. We've got an illustration of it here, and it really just maps IP address to host name. You can see we've entered a fictitious evil site mapping here just to sort of illustrate the purpose. The rule that we're going to build is very straightforward. It's going to look in that target location that we mentioned where the host file is saved in that driver's etc folder. Notice we do double escape on the rule for the backslashes. This is syntax related to Yara, and we do apply the no case modifier to it. So we just trigger on this particular file being found when we run the rule. So a match condition is a reference to that path location. You can see here we test it, and throughout this course we've talked about positive and negative testing. This is a really good example, an easy case for doing both testing. A moment ago we mentioned the escape, the double backslash. That's not present in a normal regular Windows path statement. That's just syntax related to Yara and how you have to write and specify the rule. However, if we leave those double backslashes in our test file and we run our test rule against it, we won't have any matches. That's an example of negative testing, where you want to supply input that you expect to fail, expect not to have a match, run your rule, and then prove that there was in fact no match there. Our positive testing would be when we remove those double backslashes and specify the Windows path as you would expect, when it's properly pathed out. At that point, we run our Yara rule against it. An example of positive testing here, we get a result back because we do have a match on that particular string. So just a small timeout to illustrate positive and negative testing. Keep in mind the power and the importance of the host file in this example, the power that it might give an attacker if they are able to manipulate it and add an entry. So definitely something that you want to be aware of, and this is one way that you can construct a Yara rule to trigger and alert you to that. In this lesson, we are going to explore one of the tactics that a very popular attack framework uses in order to turn off protection on a target host. It would be disabling antivirus and other host-based protections. If you think like the bad guys, then what do you want your malware to do? Maybe you want to lower the shield, so to speak. You want to turn off antivirus and other host protections on a target system. And that's exactly what some forms of malware do. In fact, the Metasploit framework actually contains a Ruby script called killav. And the whole point of this is to turn off different functions that are associated with the antivirus and the protection of a host, therefore lowering and diminishing the security posture of the target. You can see on this slide, we've actually given you the path to where that killav Ruby script is. And you can see the first few lines of it are basically the setup, and there's a reference to where a particular text file is for the configuration. And this text file is a list of antivirus and host intrusion protection system executables. That's what's contained inside that text file. So if you have Metasploit installed, you can go find this file yourself using this particular path that we have here to the Ruby file, and then dig deeper, and based on your particular configuration, the location of that AV-HIPS executable text file, that may be different, but that's what you're looking for if you want a list of a number of different antivirus software executables and protection executables. So the inspiration for this script, really came from that Ruby script with Metasploit. And what we do for our no AV rule, and this is all built around being able to detect references to turning off antivirus and those protections. We list out a number of files, line 9 through 12, coming from that Ruby script and the associated resource file. These are all files that are executables that are associated with some type of protective agent on Windows systems. Now, Of course, if we find any of these in a file where we would not expect it, or in a process that's running where we wouldn't expect it, then that's a trigger condition for us. So line 26 sets that up. A match on any of these will trigger the rule. You can add to this list. It's a structure that can easily be expanded upon. If you go ahead and run it, you can see that we've got a static file that contains all of those references to the exe files, and we have matches. So a pretty standard Yara rule execution against a static file. So keep in mind that the bad guys are always crafty, sneaky. They're going to try to do things to improve their position once they compromise the system. And one of those techniques is to run a script like what we see with Metasploit in order to lower those defenses. And if we can pick up on it, if we can detect it earlier in the cycle, then we have time to take steps and understand the attack pattern and how to defend against it. In Windows, services are essentially executables that act as a background process. Typically, they start up at the same time that the Windows operating system does, or technically shortly thereafter, and they will provide background capabilities and processes that are running to facilitate a lot of the functionality of the operating system or provide other application services. Oftentimes, malware will attempt to maintain its existence or persistence on an operating system by disguising itself as a service. The objective of this lesson is to develop a Yara rule that can detect either in a file or a process whether there are references to commands that would indicate that this is a piece of malware that is trying to configure an executable file as a service. Within Windows, the ADV API 32 is a system-level DLL, and it is one of those components that can be used for good or evil. It is intended to be able to allow that interface so that services can be managed. They can be started, they can be stopped, they can be queried to determine their status, all of this programmatically. One of the capabilities it also provides is the ability to create a Windows service. So if a piece of malware is attempting to disguise itself and hide and get that persistence by configuring itself or an executable as a service, then it might try to leverage this DLL in order to accomplish that goal. The commands that the ADV API 32 provides are create service, control service, start service, service query status, and so forth. We will build a Yara rule that allows us to identify when this particular DLL is referenced and the commands that are associated with it. So the concept here is that we're going to look for a reference to ADV API 32 DLL and a reference to one of the following commands: create service, control service, start service, and query service status. Now, it's important to point out that technically all we really need to do is look for the presence of the DLL and the create service command, and that's enough for creating the service. But keep in mind, there are a lot of other ways that you can create a service. So aside from just including these other commands for information and illustrative purposes, there is a value here, because if that service is created in another way, and then one of these commands is issued through that DLL in order to perhaps query the service status or start it, this would fire on it. So you've got a little bit of mixed coverage here if you follow this pattern that we've outlined in this particular rule. And the key is, on line 9, we define ADV API 32 DLL as a file, no case, and this is that reference to the DLL file. Lines 10 through 13, C1 through C4 on our variables, those are the command references that we're looking for. Now, the condition is set up to fire when two things happen. We find a reference to our DLL file and a reference to one of those command strings, so it works in conjunction. If those conditions are present, the rule will fire. And here we've got a demonstration in the lab where we've got a static case file that contains the strings that represent the file and the commands. And when we run our rule against it, we see that we have hits. As always, there are a lot of different ways to approach some of these tasks, and what we're showing you here is just one of those ways. There are many ways to create services. This is one, and this is one way in which you can detect that. Certificate injection represents an attack on trust. It typically refers to a process where there's an unauthorized installation or manipulation of the digital certificates on a system. This could be replacing them or installing new ones from an unauthorized perspective. And this, again, is a breach of trust. It eliminates your ability to ensure the authenticity and the integrity of your communication partners. Digital certificates are important to trust. It is one of the most crucial elements of communication over the internet. We use it to make sure that we know who we're talking to, whether it's a website, other pieces of software, or online entities such as Internet of Things and other devices. Injecting certificates when you don't have the proper authorization can have some pretty significant impacts. There's compromise in the confidentiality area and also the area of integrity in terms of your communication. If you were to perform a certificate injection attack, there are 3 things that you would have to do. You would have to make use of the Crypt32 DLL. You would have to know where the certificates are installed, and then you would have to issue the cert open system store command within the Crypt32 DLL. If you can do those 3 things, you may be able to inject a certificate. Of course, there are also controls around permissions and access. Assuming that you have elevated your permissions to the degree needed, you could inject a certificate and inject that element of mistrust in the communication process. The rule that we're going to build is going to be based upon those 3 things that must be accomplished. Crypt32 DLL, location of the certificates, and the command to open that certificate store. So first on line 9, we have a file reference to crypt32.dll, no case modifier applied. Then on line 10, we identify where the certificate store is located, and this is a registry path. Notice that we've escaped the path, the double backslash characters. This is in the rule, not the actual reference, just Yara syntax. Again, the no case modifier has been applied. And then finally, we have to meet the condition of being able to issue the cert open system store command. That's accounted for in line 11. Now, all 3 of these things have to happen. Therefore, the condition on line 13 is all of them. In our lab, we execute this against a static text file. Notice the single backslashes in the registry notation. That's what it would look like in the real world, and we do have a hit here. We see the reference to Crypt32 DLL, the registry path, as well as the command. A dropper refers to a piece of functionality that is oftentimes found within malware that allows the malicious software to install or copy files to different locations within the target operating system. And the reason that these files are copied to these locations are because there are locations that allow for the startup or the execution of that file, either when a user logs in or when the system boots. So they try to manipulate these locations within the Windows registry or the file system in order to place their desired executables in different locations that they will start automatically. So the rule that we're going to build in this particular lesson looks in several of these locations for references, and that would act as an indication that perhaps the file that we're inspecting contains dropper capability. We're going to look at the current version run location in the registry. That's where any command reference there would execute every time a user logs in. We're also going to look at the current control set / services in the registry. That's where services start up, so a file reference there may actually get loaded as a service. And then program / startup, and that's where programs or applications that run automatically after the system has booted up are referenced. We're also going to look at a few different file path locations, the Windows temp file location, and also the path to the folder that contains program data for all users. You can see here in the rule that we build, the first thing that we construct are the strings that represent our registry locations, and then we constructed 2 different strings that represent our file path locations. Notice the double backslash, we have to encode that inside our rule. It will only match on a single backslash in reality when the rule is executed. A couple of other locations that you may want to keep in mind, there are variations on the current version / run, is the run once and the run once EX. Run once will clear the registry key as soon as the command is run. So this is a desirable location for malware since it sort of cleans up after itself. The run once EX clears the registry key upon completion of the command. So very similar. 2 other locations that you may want to expand your rule in the future in order to look at these locations in order to follow the same pattern that we have demonstrated in this particular example rule. Notice when we run, we've got our static test file that's got our strings embedded in it, and our Yara rule picks up on each one of those and finds the match. Notice that we have a single backslash in those registry references, just like they would normally be referenced and pointed to within any other type of file or text reference. The double backslashes in our rule, they've escaped out, and we've got a match. So just want to point that out because there is a difference between what you look for in reality versus what you actually build in that rule with those escape characters. When it comes to spying on users, monitoring user activity, and so forth, there is a special classification of malware for that. We call it spyware, and this really represents a threat to user privacy. Sometimes spying on a user is the primary goal. It's the objective of the piece of malware. Other times, it's just one element of a larger malware package. It could just be one of several unwanted functions in the payload of the malware. In this section, we're going to focus on several different techniques that can help you determine if a process or a file contains the ability to spy on users. We're going to look at things like key logging, screen capture, audio sniffing, and more. From a pattern standpoint, we're really going to focus on trigger strings and code detection. You'll see in the examples that they really try to leverage some of the existing functionality on the operating system. Again, that living off the land concept, understanding that you may not want to deploy software that is overtly malicious. However, if you can build it from the ground up using components already on the system, that may work to your advantage. So we'll look for code detection and trigger strings. One of the primary methods for spyware to spy on a user is to collect keyboard data. This is capturing key presses, key loggers, and key loggers can either be hardware-based or software-based. Obviously, we're going to talk about the software-based implementation in this lesson. Typically, a malware writer will attempt to subvert standard Windows processes in order to capture those keyboard events, capture those key presses. What we're going to talk about in this lesson is how we can construct a rule to look for potential signs of this type of activity, this type of intent embedded within a target file. Now, there's a key DLL in Windows. It's called User32 DLL, and it's used to manage a lot of the standard functions that we're familiar with. The desktop, Windows, it handles input from users, and it's a really important key part of the operating system. Because of this DLL's ability to interact with and capture information from the keyboard, it makes it an excellent target for malware developers. They'll use this file and they'll exploit it for their own purposes. And this typically takes the form of implementing some form of software-based keylogging. The typical attack pattern would be to reference the existing file on the operating system, fly under the radar, lay low, use User32 DLL to execute the commands that you would need to capture the user key presses. That data would then be sent real-time to the attacker through a covert network channel, or those key presses could be collected and saved as a hidden and encrypted file, then sent through a covert channel at a later time. In either case, User32 DLL commands and functions that we have to be aware of would be the get async key state, map virtual key, get keyboard type. As all of the names indicate, these are all functions related to capturing keys, the state of them, and understanding the keyboard that's in use. So we're going to write a Yara rule that will be built to look for the presence of these values. And as we've said before, there are many ways to write functionally equivalent code. There are many ways to approach a single problem. This rule works with User32 DLLs and the associated commands. There may be other approaches that this rule would not capture. So make sure you understand the concepts behind this so that you can not only use the rule that we present here, but also develop your own to address other situations. That being said, the rule that we have written makes use of a match against the file, User32 DLL, and any one of those key-related commands, whether it's get async key state, map virtual key, or get keyboard type. All of these are in scope. So it triggers on the presence of the User32 DLL file being referenced and any one of those commands. When we execute it against a text file, we'll use a static text file containing the reference to the User32 DLL and then each one of those keyboard-related functions. The rule tests out, we have our matches. If you want to perform a negative test, just adjust your static file as appropriate for your test conditions. A useful technique in spying on users is to implement screen capture. Malicious software will sometimes spy on victims and attempt to capture screen content. And the goal of this lesson is to write a rule that can help detect this type of intent within a file that we're inspecting. We've already looked at the User32 DLL and its functionality. It's core to the Windows operating system and manages a lot of the interactions between a user and the operating system. And because screen management is one of these fundamental features, User32 DLL plays a large role in rendering screen space as well. And just like with keylogging, bad actors can leverage this in order to grab screen captures. The other approach that we have is to use something called GDI. This is the graphics device interface, and this is the layer that sits between the user and the operating system and the direct hardware. Instead of applications having to interact with hardware directly, GDI mediates this interaction with the device. It allows many different hardware devices to be compatible with the operating system. So as you can imagine, functions in this library can also be leveraged in this case for unauthorized screen captures. In either case, the functions that we're going to look for will be the BitBlock transfer function and getDC, that's the device context. The BitBlock transfer function performs a transfer of color data, bitblock by bitblock, corresponding to a rectangle of pixels on the specified screen source. The getDC function returns a handle for a device context, and along with that is the specification of a window or the entire screen for the capture. So you can see how these functions play into building a screen capture type capability in your malware. So we're going to write a Yara rule that's going to look for the presence of these values in a target file. Just keep in mind, this is one approach. It's not an end-all be-all rule that will always detect this type of activity. It's specific to malware writers that leverage User32 DLL and the GDI 32 DLL. This is one example of how you can do this. In the rule, lines 9 and 10 are where we set up a reference to our GDI 32 and User32 DLLs. These are both going to be string values that we search on. And then lines 11 and 12 is where we set up string values for the two functions or commands, the BitBlock transfer and the getDC. The condition indicates that we first have to find a file reference to either User32 DLL or GDI 32 DLL. Once we have a reference to either one of these dynamic link libraries, then we look for a reference to the command or the function. So it's an AND condition. We have to find one of those DLLs and one of the commands. And keep in mind, context. This is very important. If we take a screen capture, it may be a completely innocent function of a given piece of software. However, if you're inspecting an unknown piece of software, a piece of software or file that is suspect, and you discover this type of functionality, and you discover functionality to establish a covert network connection or to capture key presses, then that starts to raise the potential for malicious intent and needs to be noted. So context is important. Other findings are important. When we run this, you can see that we have a static text file, and that contains all of our test strings. We apply our rule, and we see the matches. So this is a positive test. If you wanted a negative test scenario, then modify your ytest.txt file, remove one of those conditions, remove the DLLs, add additional content after you've removed the content that should trigger, and do your negative testing that way. A capability of some unwanted malware is the ability to capture audio. Sometimes this is referred to as the ability to perform audio sniffing. The Windows Multimedia API, winmm.dll, win for multimedia.dll. This is a dynamic linking library that is a key component of the operating system. And the purpose for this file is to provide applications a way to interact with the capabilities and the resources linked to multimedia devices. Inside this file are a number of different functions that can be used by applications to interact with audio devices, whether that's to open them, start reading, manage the buffer, and then close out that session and close the device. If a piece of malware were to be designed to capture audio, then leveraging these functions would be a valid approach because your core Win Multimedia DLL file is present on the operating system. You just have to be able to identify it, load it, and manipulate the functions, be able to call those. And some of the key functions deal with handling the audio wave, starting, resetting, managing the buffer, opening and closing both the file and the device. So we're going to build a Yara rule that's going to look for these types of indicators in conjunction with the win multimedia.dll file. You can see here that we have a file defined on line 9 that is our multimedia DLL file, and then we've got 5 different commands: wave in start, wave in reset, wave in add buffer, wave in open, wave in close. All of these represent various commands managing the state, status, and buffering of the audio capture. So what we want to do in the condition then is match on a reference to that Windows Multimedia DLL in conjunction with at least two of the commands. And when we run this against a static test file, we can see that we start to have matches. We've been able to identify all of them. Obviously, you can mix and match a little bit. You can create various test files within your own lab in order to simulate different conditions and do both your positive and your negative testing, and also vary on the number of hits and matches that you find. However, this is a valid approach for finding files that make reference to this Windows Multimedia DLL file and start interacting with the various commands. If you see this inside a file that you're inspecting, as always, look at it within context, do your evaluation, collect as much data as you can, and that will help you ascertain the true purpose of the file. I think just about everybody has used the Windows Clipboard. It's a very convenient aspect of the Windows operating system, and its whole purpose is to allow you this form of temporary in-memory data storage that you can place content in, copy it into the clipboard, and then later when you're working with another application or you need to recall that data, paste it out of the clipboard into your current application. So this is all about data handling and in-memory storage of that data. And if you come across a file that contains references that might indicate that it could be interacting with the clipboard, this might be a red flag for you. It all depends upon the context. But this lesson is going to illustrate a method that we can use to inspect a file for indications that it contains instructions or commands that could be used to covertly interact with the clipboard and steal any data that we may have there, or perhaps place data there for later on. The Windows API allows interaction with the clipboard. It allows you to open it, close it, read to it, write from it. So it gives you all this capability that you need to be able to interact with the clipboard and manipulate its contents. So if a piece of malware were designed to go after your clipboard content, either reading it or writing it, then leveraging these types of functions would be a valid approach. These API functions are open clipboard, close clipboard, get clipboard data, set clipboard data. And that's what we're going to search for in our Yara rule. You can see that we've got a number of strings defined here on lines 9 through 12, and it encapsulates all of those different commands. C1 and C2 are references to establishing and terminating that session with the Windows clipboard, and then C3 and C4 are the read and the write operations that get clipboard data and set clipboard data. Now, the condition that we're going to apply in this rule is that if we find any of these strings, if we have any match on any of them, then we're going to trigger. So any occurrence would cause the rule to trigger for us. And of course, within the lab, when we go to test this, we are expecting to see this rule trigger given the content of our static text file. It includes all of those different commands. And you can see when the WinClip Yara rule is applied to it, we have our matches. Remote access tools, sometimes referred to as a RAT, they can also be referred to sometimes as remote administration tools. The reason is that remote access to a system is probably one of the primary goals of malware. The objective is to establish and maintain connectivity from attacker to target. And oftentimes we find that tools that are designed to allow legitimate remote administration of systems are actually taken advantage of, and they're subverted and turned into tools of the attacker. Now, this can be done through exploiting a misconfiguration. That would be an error in the configuration of the operating system or application, or by directly manipulating the base operating system services and applications. Using this knowledge, we are going to approach writing our Yara rules in three ways: references to tools, code to call or invoke a tool or command, or related string values. We're going to look at all three of these over the course of the next few lessons as we look at remote access tools, how you can detect them in processes and files. VNC is a remote access tool that has been around for quite some time. It is certainly not new to the scene. VNC actually stands for Virtual Network Connection, and it's a graphical desktop sharing product. It uses something called RFB, the remote frame buffer, to remotely control another system. And like many other remote admin tools, it can be used for good or evil. As a security professional, you would likely want to know if a given file contains instructions to start up and manage a VNC session. The rule that we're going to write in this lesson really keys off of three things: the reference to the vnc.ini file, which is the configuration file for the software, and then two commands, start VNC and stop VNC. So if we see any of these in a file, we know that we have to take a deeper look at it. Attackers would likely abuse VNC to perform all sorts of malicious actions as a logged on user. This could include opening documents, downloading data, running arbitrary commands, even using the compromised system as a pivot point to dig deeper into your network and compromise other systems. So we want to be tipped off to this as soon as possible. The rule that we're going to build here is shown on this slide. We define one file, ultravnc.ini, that's on line 9, and then we define two commands, start VNC, stop VNC, that's on lines 10 and 11. The condition that we build here is a match on any of them. So if we find the ultravnc.ini file referenced, then that means we could have a situation where the file that we're inspecting attempts to make use of that INI file. Find out if it's present on the machine, which would indicate the presence of the VNC executable. Read the settings from it, or potentially even add the file in the software. Of course, the start and stop VNC are commands that would reference an effort around managing the running state of a VNC connection. Testing this is easy. We've embedded the search strings in a test file, and then we've run our vnc_rat.yara rule file against it, and you can see the matches. As with any of these, vary your files accordingly so that you can have both positive and negative testing and a variety of different test scenarios. Another common remote access protocol and configuration is RDP. This is the remote desktop protocol. It used to be called Terminal Server, Terminal Services from Microsoft. So you'll still see a lot of old references or backwards references to that technology, even though we're talking about RDP. RDP is the remote desktop protocol, and it allows users to execute remote operations between network connected systems. In some cases, this is likely undesirable or would be a security concern, in the sense that an attacker could attempt to leverage an RDP connection for remote control or data extraction purposes. The rule that we're going to build looks for signs of RDP configuration or use, and this is going to be a multi-value search, and we're going to look for references in a variety of different locations and forms. They could be registry paths, registry values, or commands. You can see outlined on this particular slide, the first three items that we're going to look for are all registry paths. These all deal with the presence of terminal server RDP services being installed and active. The fourth one, enable admin TS remote. That is a registry value that we're going to be looking for. And then, of course, the net start and the SC service control. These are different commands that could be used to start up a terminal session or an RDP session. This is all going to go into the rule that we build here, and you can see in our code lines 9, 10, and 11 outline those registry paths. Line 12 is our registry value, enable admin TS remote. And then 13 and 14 define those two command strings, the net start term service and the SC config term service start. The condition triggers on any of these. So if we find any of the registry paths, any of the commands, we're going to trigger a match. Now, there is one thing that we have to point out here. In those registry paths on lines 9, 10, and 11, notice the double backslash characters. This double escaping is needed based on the rule syntax, but it would not be present in the actual location or even in our test file. And you can see here we've got a static test file that we're using, and we only have that single backslash character. It's all related to the syntax of the rule, and we need to do that double escaping. So, as always, modify this file in order to support both positive and negative testing, as well as a variety of different scenarios so that you can test out your rule and see how it might operate in a production environment. The Telnet protocol is one of the original internet communication protocols. It allows for two systems to connect and have a virtual connection to a terminal. It allows a user at the client to connect to a server or a network device and establish what amounts to a command line type interface. At that point, the user would start to issue commands to interact with the remote server. Obviously, this presents an opportunity for malicious software to take advantage of Telnet services. When Telnet services are installed on a Windows system, the path in which these components are placed is in software/Microsoft/Telnet server. The Yara rule that we're going to look at in this particular lesson will help us identify if this location is active on a Windows system. Software that intends to make use of Telnet for communication purposes, and these are probably unwanted communications, may make a reference to this location to try to see if Telnet is installed, or possibly even to try to force some sort of installation to that location. The rule that we're going to develop will look for a reference to software/Microsoft/Telnet server. You can see here we set that up as a string in line 9, very straightforward. The only catch is the double backslash. We have to escape this in our Yara rule. In real life, there would only be a single backslash, and you'll see that in our test file where we embed just a single backslash there. But for the rule, in the syntax of Yara, we have to make sure we do that double escaping. The condition is very straightforward. It's just a hit or a miss on this particular string value. You can see with our test file, we do have that single backslash embedded there. When we run this particular tool against the rule file, we can see that we do have a match, and it shows that direct reference to that path location. One of the remote access type scenarios that you need to be aware of is software that remotely accesses a webcam in order to capture video content. The lesson is going to be centered around helping you determine if a file contains indications that it attempts to take remote control over a webcam. The ADP Cap32 DLL is a module inside Windows that can be used for legitimate purposes, such as capturing AVI movies and capturing content from web cameras. However, this DLL can also be used for malicious purposes if it's loaded as part of a malware package. The AVI Cap32 DLL contains a command called create capture window, and this is the command that allows the capture of video content. The Yara rule that we're going to build is going to look for a combination of a reference to the DLL file and the command itself. The rule that we will develop for this is a basic search on all strings that are specified inside the rule. On line 10, we set up a reference to a particular file, AVI cap32.dll, and we assign that to the variable $F1. On line 11, we do the equivalent for the command, the create capture window. We assign that a variable $C1. We also specify no case on both. And then our condition is all of them. So we have to have a reference to both inside the target file in order to trigger a match. When a match is triggered, you'll get a result like we see here with our testing. We've got a static file that contains a reference to the DLL and also the command. When we run our Yara rule against that particular file, we see a hit. We see a match on both of them. So there are a number of different ways to take control over a webcam. This is just one of them, and this rule can point you in the right direction in terms of detecting that type of activity within a file. Welcome to the section on cryptocurrency, P2P, and ransomware. In this lesson, we are going to talk about several different types of software. One you certainly don't want in your environment, that's ransomware, and then some others that are a little bit more debatable. It depends upon your environment and your tolerance for risk and software processes that may not follow your business practices. That would be cryptocurrency mining, P2P sharing networks, and private browsing through Tor. So we're going to cover all these topics in this particular lesson, and the way in which we're going to go about doing this is following the patterns that we've established through the course here of looking at the file structure for embedded commands, code detection, looking for those commands or code embedded within a particular file, and also any strings that are of interest to us. So if you just think about these types of software and what it might mean to your environment, clearly there are things that you would want to know about. Ransomware, we know the evils of that, how prolific it is, and the damage that it can do. But also, P2P sharing tools could represent a threat to your network, from unauthorized sharing of data, files, copyright material, and so forth. Also, from a resource consumption standpoint, crypto mining, that could become a problem for you as you start burning resources to support a mining operation. Again, not your typical business practice, probably something that you want to be aware of on your network. So let's go ahead and jump into this section. We're going to have a couple of lessons on P2P sharing, one on ransomware, another on private browsing. One of the main components of ransomware is demanding payment. And this is where the bad guys shake you down, they extort you for money, and they use some sort of language embedded inside the ransomware that will compel you to make payment. Of course, that is very handy for searching for strings. These ransomware components typically contain a number of different common phrases, and these phrases are to describe either the state of your files or to demand payment. And the goal here is to create a Yara rule that will help detect the presence of these phrases. And the approach is pretty simple. We're going to put together a list of strings, and these strings are going to form the search for different words or phrases that will be used to communicate the nature of the attack and also describe how we should make payment in order to get our files and our data back. Any words or phrases that you can associate with an attempted extortion are likely valid strings. We've got a list here just to kind of get you started. By all means, expand this as you see necessary. And the strings that we have right now are: your files have been encrypted, restore your files, to make payment, unless you pay us, and transfer money. The Yara rule that we're going to build is all around looking for the presence of these strings inside a target file. The rule is pretty basic. It's string detection based on these phrases combined with a condition that it should be applied against executable files only. So line 4 is where we set up our rule. Line 5, 6, and 7 define the metadata around the rule, and it's a typical description and a version number. The strings on lines 8 through 14 represent these common phrases. As we mentioned before, expand this as necessary. Try to think how somebody may demand money from you, or how somebody may describe the steps they've taken to hold your system hostage, to hold your data hostage. All of those would be good values as well. Keep in mind that this method of detection is a lot like using a password list. It's only as good as your list. So you want to make sure that you've got the variety and the coverage there with those strings so that you can make sure that you hit on multiple different scenarios. 2 other adjustments that you can make would be obviously adding string values for the description of what's happened to your system and varying the match requirements in the rule condition. Here we have it trigger off of it being an executable file and a match on 2 of those phrases. Vary that as you see fit. When we run this, we use our dynamic test file. It pulls those strings in from a outside text file as a resource, pulls them in. We have it operating, in this case, with process ID 4164. We run our Yara rule against this, and we start to see those memory locations now, where those strings show up and where there's matches. Tor is the onion router. The onion router, or Tor, is not necessarily malware, and it's not on its own evil. It's a tool that you can use if you want to increase your level of privacy during your time online. Like many of the tools we talked about in this course, Tor can fall into 2 categories. It can be used by bad actors to set up a covert channel, or simply maybe a piece of unwanted software in your environment. You'll have to make the decision on that, whether you want this piece of software in your environment or not. So, assuming that this is something that you want to detect and look into, up front we need to level set everybody and say, Tor is difficult to match with patterns sometimes. And the reason is that Tor is built on top of Firefox and Mozilla components. It even uses OpenSSL for encryption purposes. All this means that the conditions are ripe for false positives. If you look at Firefox.exe, SSL EA32DLL, modsglue DLL, these are all common files that Mozilla Firefox use and other open source tools. It can be easily confused with Tor from a pattern matching standpoint. So we're going to change things up, and we're going to look for 3 different strings: onion, .onion, and Tor project, assuming that we can reduce false positives by looking for these strings. That hypothesis may be true, it may not be, but given the nature of the high probability of a false positive, this may be an alternative way to search for presence of Tor within files and processes. You can see here that we build a regular expression on line 10. That is where we use an OR condition essentially to concatenate a series of conditions together that string needs to match on any of those conditions on line 13. The /I flag on a regular expression indicates that it should be matching with case insensitive. And when we go to the lab, we can construct a static file containing those strings, execute our Yara rule against it, and then see those matches get returned as output from Yara. Again, Tor May or may not be something that you want on your network. Depends upon your organization and your policies. Likely not. If this is something that you want to detect, enter into that activity knowing that there is a high likelihood of false positives. However, this alternative approach may be useful. In this lesson, we're going to talk about mining for Bitcoin. No, we're not going to mine, but what we are going to do is detect files and processes that may have the capability of acting as a cryptocurrency miner. Bitcoin is cool. You probably don't want it on your network, though. The way we're going to approach this is to do a string-based search pattern match for phrases and words that you would typically see in crypto mining operations. As always, this is a starter set of rules. It's a starting point. After you get your initial rule to function and operate and run, then consider expanding or enhancing the list. That way you can catch more crypto miners. The strings that we're going to use reference some common files and just trigger string values that you would associate with mining. OpenCLL DLL, OpenGL32 DLL, Bitcoin Stratum, and so forth. You can see how you can really add to this list. It's a starter set. Take this as your base and then move forward with it. The rule that we have is fairly straightforward. We have two different files defined on lines 9 and 10 with no case modifier applied. I want to pay particular attention to line 11. That is another file, OpenGL32.dll. That is another file that is defined here, but just keep in mind that not all files are directly tied to cryptocurrency. OpenGL is an example of this. It's a file that supports imaging, graphics, and GPU access, and you can use this for a variety of reasons, not just an interface to use the processing power for your crypto mining. Following that, on lines 12 through 16, we have a series of string values that we will be searching for. The condition is on line 18. It says that one of any of those files, F1 through F3, and one of any of the search strings. So it's sort of a combination condition with an AND in the center of two different conditions to evaluate. One of those files and one of those strings will trigger. So as we move into the lab, we create a static text file containing the string representation of the trigger strings in the files. We execute our miner.yara rule against that, and you can see that we have matches. As always, positive negative testing is key here. Make sure that you prove out in your own environment the validity of the rule, and then seriously consider expanding upon this. P2P, or peer-to-peer networking, is a very powerful technology. It's been around for a little while, and it may be more prevalent than you even think, because behind the scenes, there is a lot of connectivity in many applications that provide this direct peer-to-peer communication capability. P2P networking, it gives you that ability to send data from one system to another more or less directly. And this is an excellent way of transferring data, files, even messaging in some cases. So in a corporate environment, this type of activity may not be wanted. And this lesson is going to focus on how we can build a set of rules to look for references to several of the more popular P2P networking products. The rule is going to be built around a standard string search, but you'll see in a moment the way we implement it is going to be a little bit different from some of the other ways that we've approached string searches in this course. We are going to build a series of regular expressions that are coupled or chained together in order to look for these values. Now, the values that we're going to be looking for would be strings that are appropriate or oriented with different products that provide peer-to-peer networking. It would be torrent, P2P, peer-to-peer, N2K, magnet, and Shariza. Very common terms that you may see out there with different products. Obviously, expand this list as you see fit in order to give you the coverage that you need. So from a basic string detection standpoint, we're going to change things a little bit. Look at line 9. This is the key to the whole rule here, and it's a really good example of how flexible Yara is when writing and applying searches. This line is really the setup here. We build out a string expression that's really just a regular expression. You can see the forward slashes. That indicates the fact that it is a regular expression there. We have deviated from our naming convention a little bit just for clarity. This is our P2P strings, and it's going to be a series of strings. The pipe symbol, that indicates an OR condition. So when this rule is applied, we're looking for torrent or P2P or peer-to-peer. You get the pattern here. Every one of them is coupled by that pipe symbol indicating a logical processing. Look for an OR condition. Now, one other thing to point out is the I flag. That makes it a case-insensitive search. Very important because we don't always know how these strings are going to be represented. P2P is an excellent example. It could be lowercase like we have here in our rule, or it could be two uppercase P's. The /I gives us that case insensitivity. Now, the condition is set for any of the strings. If we have a match on any of them, then we're going to trigger and we're going to flag it. Here in the lab, we've got a static test file that contains each one of those values. And when we run our Yara rule against it, the regular expression is active. It's valid. We see matches returned from the rule when it executes. Go ahead and modify this test file in your own lab environment. Do positive and negative testing. See if you can chain additional regular expressions to this. In the last lesson, we took a look at different types of software to provide P2P capability. But there's also another way for applications or even malware to implement peer-to-peer networking functionality. It is to make use of the Windows operating system and the APIs associated with it. It's do-it-yourself P2P networking. The Windows platform has a number of development APIs that give developers support for when they want to write their own P2P applications or embed those capabilities within an application. If these functions are present in a process or a file and we didn't expect them to be there, then that might be an indication that there's an issue here that's worth a little further investigation. The approach that we're going to use is to look for a series of commands that map back to the Windows p2p.h file. This is a header file. It provides a series of interfaces that sit between the application and the underlying Windows operating system APIs. It gives you that ability to issue a call to those APIs in a programmer-friendly way. And these calls all support peer-to-peer networking references. You can see a list of the strings that we're going to look for here. They all start with peer collaborate, and then there's a pattern here where that prefixes the name of the command or the function that you want to invoke. So very developer friendly. Now, our rule could look for all of these, but we're going to take a shortcut here. And the shortcut is based on that naming convention. It's based on the fact that the list of interface functions all have this very similar naming convention. And that's what we're going to use with our Yara rule. Each function starts with the peer collab as part of the name. That's the common denominator in all of them. So knowing that a Yara rule will match on portions of a larger string, we can use that to our advantage. That means that on line 9, we're going to define just a single search string, C1 for command 1, and it's just going to reference that peer collab, that common element that stretches across all of the names of all of the different functions that you could call. The result of this is basically a peer collab.star, sort of like a wildcard representation of it. And of course, our condition on line 11 would be to match on any indication that we found a C1 pattern. In the lab, you can see that we've got our do-it-yourself P2P Yara rule there on Y-test. We've got our content, and when we run that, we start picking up on matches. Of course, the display shows that match on peer collab because that's the string that was matched. That is all based upon the fact that if there are any peer collaboration references inside a file, then you want to look deeper. So that would be a file that you want to inspect at another level. So aside from just looking for products, there are ways that you can look for peer-to-peer networking capability embedded within files that were built specifically for the Windows operating system using some of those hooks and those calls into those API functions. So far in this course, we really haven't referenced too many of the common hacking and exploitation tools that you're probably familiar with. We haven't talked about Metasploit, we haven't talked about Nmap, and so forth. That's going to change with this lesson. During this lesson, we're going to talk about how various forms of malware might make references to these types of tools or system commands that will be present on a target system. Now, that could come from a couple of different situations. It could be that the tools maybe already be available on the target system, or the malware could be acting as an installer, setting the stage for what's to come. So we're going to look for two main things. We're going to look for string matching and file analysis. We're going to look from a file analysis standpoint at common tool names and command references. From a string matching perspective, it's going to be looking for those embedded commands or other strings that may be of interest, may reference some unwanted activity. So we're going to look for the presence and usage of Nmap, Metasploit, some of these common tools. We're also going to look at different shells. This could be started up through something like Netcat, or it could be a custom shell that's implemented as a web shell, giving the attacker access through a web application in order to get that shell on the target system. So we'll inspect files for all these different types of conditions and show you some examples that might be useful in your environment. If you've spent any time in the networking world or working with pen testing teams, you are probably familiar with Nmap. This tool has been around for a long time, and part of the reason that it's been around for a long time is just how effective it is. This is an excellent tool for mapping networks. And if you find it in your environment, if you find a process running that calls this particular utility or a file that makes a reference to it, then that's likely an indication that there's some type of network mapping capability there, and you want to dig deeper. You want to understand exactly the threat that it may present. What we're going to do with this particular rule is straightforward. It follows the pattern that we've outlined a number of times in this course, where we're looking for string references to executables or values that may be associated with the Nmap tool. It would be nmap, nmap.org as a reference to the website for the utility, and ZenMap, which is a GUI overlay to the Nmap tool. And it's also important to keep in mind that while a lot of the focus on Nmap is network mapping, there is also a component to the tool called the Nmap scripting engine, the NSE. And this is a scripting capability that has been built into the Nmap tool. Scripts are embedded inside a text file, and then they are given the .nse extension. And when you call that particular .nse file with Nmap, the script will execute. And through this engine, developers, researchers have added a lot of enhancements and a lot of capabilities to the Nmap tool. So not only does Nmap do network scanning and mapping activities, but it can now also execute scripts that can scan for vulnerabilities. There's a lot of functionality inside this tool, and a lot of it has been greatly expanded upon by the NSE. So our basic rule here is illustrated with the screen capture at the top of this slide. You can see we've deviated just a small bit from our normal naming convention. We've got Nmap string 1, 2, and 3, and it represents those 3 different strings that would be associated with Nmap, either the name of the tool itself, a reference to the site where it's maintained, or a reference to that user interface, that UI that's overlaid on top of the Nmap tool. A moment ago, we mentioned that the scripting engine component of Nmap allows you to extend the capability of the tool. The second rule that we have outlined here is just a very simple rule, but it illustrates how you can use Yara to look for files with an extension of NSE. So if you pass a set of files to Yara for evaluation, you may want to consider having this rule embedded somewhere in your rule chain. And line 6 is really where this works. Obviously, we define a string for the file extension as NSE, but our condition on line 6 checks for file extension and then in parentheses, end of file. So we're looking for that NSE reference at the end of the file, and that's an indicator that we've got an NSE script on our hands. If we just test our basic rule, we can use a variety of different techniques, whether it's string 64 or creating a dynamic EXE. In this case, for illustrative purposes, we've just used the static file approach, and you can see that we get a number of hits. So a couple of different techniques and approaches to dealing with looking for references either in a file or a process to the Nmap utility. The Netcat utility is a tool that can be used to open up network connections between 2 different hosts and move data between them. Obviously, this has a lot of capability in terms of troubleshooting and managing a network, but it can also be used for less than honorable purposes, and that's what we've seen develop over the years. One of the things that Netcat can be used for is to create a reverse shell. This is a situation where you have an attacker and a victim. The attacker sets up a listener with Netcat on their system, and then the victim, who also has Netcat installed on their system, basically phones home. It calls back to that attacker. That's why it's called a reverse shell. And once the connection is made, a command prompt is spawned on the victim system. This allows the attacker to interact with that shell and execute commands. So obviously, if we have a file that makes references to Netcat, some of the commands, then we want to know about it, and we need to put together a Yara rule that will help us detect these types of string patterns. You can see on this slide, we give you the syntax for the attacker system and also the client or the victim. You can see on the attacker side, they set up the listener by calling netcat or ncat, followed by the -L, the -P, and a port reference. On the victim side, they run netcat, and they reference the attacker's IP address and port that's being listened to. And then there's the --exec cmd.exe. This is what actually spawns that command shell once the connection is made. So we're going to build a Yara rule that looks for several different things. nc, ncat.exe, and netcat. These are all variations of the netcat utility and how it's named. Then we're going to look for a comment reverse shell. Then we're going to look for two variations of netcat acting as a listener. And then we're going to look for a string that represents the command.exe being called with the --exec parameter. You can see here that we set up all of the references to the common file names associated with netcat. That's our P1, P2, and P3. The rest of the strings, S1 through S4, represent a comment reverse shell, along with the different variations of setting up netcat as a listener, and then also the --exec cmd.exe for spawning that command shell. This script may need to be revised. The netcat binaries can be renamed, they can be modified, all sorts of different alternative names can be used, so the script needs to be customized in order to look for those types of situations just based on what you're targeting. Keep in mind you always want to test your rules against a malicious sample as well as a benign sample. That way you can show the positive and the negative testing. Here we've got our test file that has all of the different string values loaded up in it. And then when we run our rule against that particular test file, we start to see those matches. So this is just one way that you can inspect a file looking for the presence of various netcat commands. A very common task for threat hunters is to look at their web servers and look for files that may actually be web shells. Web shells are a very dangerous type of script. Attackers will use a web shell in order to establish essentially a command shell on a web server. These are malicious scripts that are used after the compromise of a web server through some other attack. The attacker gets a foothold on your system and has the ability to write files to your web server or upload files to your web server. This is the first step, is to actually penetrate that system. The second step would be to install the web shell. And the web shell, as we mentioned, is really sort of a back door. It allows the attacker to get a connection to that system and basically a command shell. The attacker would then interact with the shell over HTTPS, the web nature of it, and would begin issuing commands to carry out and view the results. So sometimes web shells will attempt to hide their functionality, and one of the ways in which they do this is to use base64 encoding and decoding for their instructions. This brings into play the eval function. That way it can dynamically encode or decode these base64 strings. The other indicator that you may have a potential web shell on your hands would be a reference to the Windows command shell. So these are the indicators that we're going to look for when we build our script. You can see here that we've got a command string on line 9. That's the eval command. That allows you to essentially execute a command. In this case, we're looking at the base64 decode. The command would come into the shell being base64 encoded. The shell would receive that base64 encoded command string, use the eval function combined with base64_decode in order to switch it back to an executable format that the shell can then hand off to command.exe, which is on line 10. That's the file reference to that particular Windows command. If we find either one of these, we want to trigger a match. Either one of them may potentially indicate something that we want to look closer at and validate to make sure that the file that we're inspecting is not a web shell. In our lab, we've got a static text file that contains the eval base64 decode commands, as well as the reference to command.exe. When we run our rule against it, we have a match. Always test this in your environment before using it. Make sure that you've got positive and negative test cases. That way you can verify the integrity of your rule. This lesson is built around showing you several techniques that you can use in order to identify files that contain callouts or references to PowerShell Empire. PowerShell Empire is an open source exploitation framework. It really plays into the area of post-exploitation, and it gives pen testers and red teams a lot of different tools and capabilities that they can use inside a controlled environment in order to simulate and demonstrate what could happen during an attack. It really provides a platform for these professionals to test and assess the security posture of a network. But like any tool, PowerShell Empire can be abused, and it can be used for nefarious purposes. If unauthorized individuals are using this and producing files that have callouts to various PowerShell Empire components and commands, you likely want to know about it. So we're going to build a Yara rule that looks for references to Invoke Empire, PowerShell Empire, and Empire Agent. You can see in our rule here that we've got several different string values set up. The first one is a reference to a command, and that's Invoke Empire command. That is a key command within PowerShell Empire, and if you see a reference to that within a file that you're inspecting, then that's an indication that it requires a much closer look. Along with that, we've got two string values, PowerShell-Empire and Empire Agent. These deal with just generic references to PowerShell Empire and also a reference to the agent component. You may need to adjust some of these rules based on specific characteristics that you observe during your analysis of different files, but this is going to give you a good starting point and a good base to work from. You may also want to consider incorporating other indicators, specific function names, and command line parameters and so forth. That will just strengthen the ability of this rule to detect presence of references to PowerShell Empire. Again, always make sure that you test your Yara rules thoroughly from both a malicious and benign sample standpoint. You want to ensure accuracy and avoid false positives. From our standpoint with testing, we included the search strings inside a static test file, and then we ran the ps_empire Yara rule against that particular file. As you can see, we hit on all of the embedded strings. Negative testing would include adjusting this test file as appropriate in order to demonstrate misses. A component of the Metasploit framework is a utility called Venom. MSF Venom is a payload generator and an encoding tool. As we mentioned, it's part of the Metasploit framework, and its primary purpose is to create various types of payload that are used for exploitation. It can include shellcode, binary executables, and other formats. An attacker would use Venom to generate a standalone executable file, and then once that file is delivered to the victim and they execute it, it would carry out specific actions on the target. This could range from Trojans to backdoors to all types of malicious executable activity. Clearly, this is something that we want to be able to detect. And there are several strings that are embedded within a Venom-generated file. These are strings that, once they're modified, we can pick up on and we can use as a hook and a way of identifying whether a particular file was generated with Venom. It would be a reference to MSF Venom, Metasploit payload, and interpreter. So we're going to build a Yara rule that's going to look for presence of these values inside a target file. Each one of these values we're going to set up as a string. String 1, 2, and 3 represents each one of these string sets. The condition portion of our rule is going to indicate that we need to hit on 2 of them if we're going to consider it a match and trigger. You may want to adjust some of these values based on different characteristics that you observe during your analysis and working with various files, but this is a good starting point. You may also want to consider other payloads, architecture information, or file format signatures that are associated with Venom payloads. Once this rule is run, if the strings are detected inside a test file or a file that we're inspecting because we believe it to be suspicious in nature, you will see these matches. Modify this file in order to test from a negative perspective as well, but you can see here we've got a demonstration of those rules matching and hitting and pulling it out of a static file. In the resource section of this lesson, you will find a zip file that contains all of the Yara rules that we've developed throughout the course. We also have all of the supporting files for building your own testing tools. All of the code and rules are provided as is. Please take these, use them, develop, enhance them, make sure you test them in your environment before promoting to production. And now it's time to wrap up the course. Yes, it's time for the conclusion and the summary, and we'll take a look back at everything that we've learned in the last few hours. When we started this course, we said that there were a few things that we really wanted to hit on, and I think we've done that. We've talked about what an indispensable tool Yara is for pattern matching and how it can really help security analysts and professionals. We went deep into the fundamentals of Yara, looking at the syntax and the rules and even some of the advanced features. And all of this was geared towards teaching you not just how to write Yara rules, but how to look at the threat presented by files and processes and how to build those rules in order to respond and detect those threats. And we hope that we've done it in a way that is accessible for beginners, intermediate learners, and even some folks that have a lot of experience with Yara. Maybe you've picked up a few new tricks along the way. Now, we're at the end of the course, and I think you've got a lot of insight into Yara now and how you can use that to support your malware analysis and really add to your organization's defenses. And that is really the key takeaway from this course. That's what we want you to walk away from this course being able to do. Now, along the way, we looked at the first two sections, which was really the setup. It was the fundamentals, so that we were all on the same page in terms of what we were trying to accomplish, the tools and techniques that are used by the adversaries. Then we went into the writing of Yara rules. We talked about the syntax and how to design and develop your own testing tools for your lab environment. And then we went into the meat of the course. This was the real-life scenarios that we looked at where we constructed rules in order to detect things like OS manipulation, spying, keyloggers, data collection, crypto, all of these things that you don't want on your network, you don't want in your environment, and you need to be able to detect. We showed you real-world ways of doing that with Yara. So this is the wrap-up. This is the conclusion. Thank you for taking this course. I certainly hope that it has been beneficial for you and has really added to your understanding of Yara and how you can use it for defensive purposes.